Hello, test. Oh, hi. Good morning, everybody. Welcome to day 2 of VeloxCon. It is really great to see so many of you back today. Hopefully, many of you were able to stick around for the happy hour last night. I sadly learned I missed the sushi by 2 minutes, so kudos to the folks who got the sushi. Fun. What a great first day. It was really awesome, and we are excited to do more today. Focused a lot, as you can probably tell from the agenda, on hardware and hardware acceleration and what's going on with that in this space. So before I introduce our keynote this morning, a few housekeeping items that Meta asks that I share. One, make sure you keep your badge on. If you're going to leave or walk around, make sure you have a Meta employee with you. And I think they kind of station right near the exit. So just grab anybody that has a Meta badge or Meta on their badge and ask them to walk you out. And I really encourage you all to stay. We are ending today with what I'm calling a powerhouse keynote panel, where we're going to have some real visionaries from the hardware space talking about what's going on in the space. And so we moved it to the end of the day to encourage people to stay, and we hope you do that. Okay. So with that, I am so excited to introduce Ori. Ori is one of the creators of Velox, and today he is going to be talking about Velox and the accelerated age. So welcome, Ori.
Right, just here on your left. The microphones.
Yeah, right. Okay.
It's your microphone.
Yeah. We got the first slide on.
Yes, it's the Velox and accelerator age.
Right, okay, good.
I'll be down there. Give me a signal if you need anything. The mic is in your left.
Yeah. Yeah, hi everybody. So I'm Ori from Velox, and I'll be talking about Velox futures. So we have two main directions. So we're going to the metal, as we have been doing so far. So in this case, we're going to the accelerators and the heterogeneous hardware. And then we have the opposite direction. We're going to the application as well, because we find that we need a language play as well. Like Masha, for example, yesterday was describing all these new things that should be expressed but cannot be expressed in the current languages and frameworks, so we also need to address that space. And then to the end of the presentation, I'll hope to show you that these are not contradictory directions or opposite directions, but rather synergistic directions that come together in nice and sometimes even unexpected ways. So we are at an interesting inflection point, because we are getting to the point where heterogeneous compute is very much a fact on the ground, like even a foundational fact on the ground in the AI space. It is getting validated to be also a viable solution for accelerating general purpose data management. And of course, AI is never without data. So you may have data without AI, but no AI without data. So it's kind of normal that we see AI as rising as the first consumer of data, and therefore these become adjacent in terms of process, and they will also be adjacent in terms of technology, which is where this accelerator business is leading us. So then of course we have universal penetration of GPUs in the AI space. Doing the same thing for data management will come, but it's going to require a new generation of data centers possibly. And of course, this has a precondition, the triggering precondition, that will be that the software is mature and functional, and we'll have some ideas of how we can, while representing different directions and different approaches to doing this thing, how we can work together to make this a reality come sooner. The bigger morale of this story is that this, let's say, white box AI, where we see data preparation, data management, data loading into training, inference, all as pieces of like an extended query plan. This will allow us to unlock all kinds of potential in the mix and make efficient use of tomorrow's data centers. But for this, we need to have a holistic view on the whole value chain, and we need to see it as a white box. So I'll be talking about accelerators in specific, and then I'll go to language. So let's dive into the metal. So Velox, of course, was founded with the notion of being best of breed in vectorized execution, or basically big data processing, any database-like workflow, if you like. And that has instances of it in streaming, instances of it in, hopefully soon in AI data loading, plenty of instances very successfully in regular data management, like with Presto and Spark. But really the understanding that is underlying all of these is a lot of experience in query execution, experience in query optimization, and a good understanding of the basic physics like that underlie why does stuff work and how does it actually work. And now as we turn to accelerators, we have to kind of revise our understanding and then have like a reality-based view on how that stuff works and how it should be approached and how we're going to do something meaningful in this space. So Velox as a compute ABI, David Cohen from Intel, the former big data lead, the first sponsor of Gluten, described the Velox opportunity as consisting of making Velox and the standard ABI for compute. So just like MPI and open fabrics and things of that sort became the standard ABI for high-performance compute, Velox would have the opportunity of becoming the ABI for data management. And this game is playing out quite well. We have at least 3 systems that take Velox as the entry point to compute. We have Velox itself. We have Neuroblade that provides accelerators through the Velox ABI interfaces. We have libcudf coming to the Velox world. We have our own Velox Wave, which is our GPU play. And then there's others that are Velox adjacent. There's Voltron Data, and there's a Data Pelago. I don't know if they use Velox as the entry point into acceleration, but they're certainly Velox adjacent part of the community. So we're in great company. We have Rivas, an up-and-coming hardware vendor in this space with which we've been cooperating also. So there's a lot of interest and a lot of take-up here. And so we welcome all our partners into building this next generation of data management. So next slide. So what are the basic foundational understandings that should guide us in architecting for accelerators or heterogeneous compute? So if Velox certainly is not the first, there's a good 10 years of practice in this line of work. So if you're not the first to come, then of course you have the benefit of the experience of the ones who went before, but then you also it's incumbent upon you to do something new to advance the state of the art, and so we look at the foundations on which such advance might be based, and then we'll see how far we go. So the GPU is quite different, and so the foundational, let's say, defining criteria is that you have very high internal bandwidth, like a terabyte, sometimes multiple terabytes per second of bandwidth to memory on device. You have a lot less bandwidth to host memory. Slightly depends a little bit on the architecture, but an order of magnitude less bandwidth there. Then you have pretty good networks, and then you have a device synchronization round trip from host to device of some 10 microseconds or so. And now, depending a little bit on what kind of device you have, you can compute, let's say, a computation on 500,000 to 1 million integer values in the time it takes to do a round trip. So round trips are expensive compared to everything else. So the other thing is the memory subsystem is quite different. So CPU memory is absolutely for free. You can do anything you want with memory. You can store stuff in intermediates in memory. You can do function calls. You can have function frames. You can have all of that stuff. And it costs you nothing because you have 32K or so per thread of cache. And the situation on the GPU is quite different. You might have 100 bytes of L1 cache per thread. And so you cannot count on everything hitting cache. So from this follows that you must not store intermediates in memory. Memory is no longer for free. You must also not do function calls, because function calls, heaven forbid, they make function frames and they write to memory and they read from memory, and they do that even scattered, so they're no good. So it's a pretty different platform in this regard. So CPU gets high utilization from having lots of threads, and lots of threads there means 100 threads or something like that. And you might even see negative returns if you put too many threads in there. GPU tends to give positive returns up to full occupancy, which means 100K to 200K threads, something like that, depending on the type of device. And so when you get full utilization on CPU, you get it by just having 50 threads per query and then lots of queries, and then these threads must never synchronize with the other thread. Mutexes will kill you. So every thread does its own thing, and everything goes merrily on its way as long as you have a few dozen of these threads going. GPU threading is entirely different. They side-by-side threads, in principle, should do side-by-side data. They have frequent barriers, but then you can only have barriers with the threads next to you. The other guys don't try to sync with them. It will kill you. So then it means that to have utilization, we need to have, let's say, 200K, 500K runnable threads. Maybe if threads are resident on device, maybe 100K, 200K, and then you have to have threads that are queued up. So whenever these finish, the next ones come in, and this is how you get utilization. And the only reason why you're running on a platform that's as difficult as that is performance. So utilization is key. You gotta drive utilization all the time. Okay. So next, so how do we design for that? Well, the obvious conclusions is that we must not do round trips, no casual round trips. Extract all latent parallelism, so it means that if you have data-independent columns, you do data-independent columns independently. You decode file formats, for example, all the columns in parallel. First all the filters, then all the non-filter columns. Maybe you do lazy vectors like we do in Velox, a little bit more on that later. Because the host to storage to device and host to device bandwidth is a tiny fraction of the in-device bandwidth, you must be very planful and very aware in how you time your I/O and have tons of stuff in flight. I mean, any distributed system, the performance, we like to say, is parallelism times locality, and this continues to be true here. So programming these things or architecting these things is about juggling lots of balls in flight. You got to have lots of things in flight, or rather just the right amount, because we should not, as we see, get utilization by having tons of queries at the same time, because we run out of space if we do. So looking at the trends, the compute bandwidth inside the device grows fastest. The memory bandwidth grows almost apace with that. The host to device bandwidth grows a bit slower, and the thing that doesn't get better at all is latency. So the trend is that you have to ship bigger and bigger units and do less and less round trips and plan better and better. Okay, so how do you program that? So GPU is to the unexpecting is a surprising platform, because on a GPU you pay for what you don't do. For example, you have a big program and there's pieces of program that don't run. They still cost you in terms of register pressure, in terms of maybe allocating shared memory and resources like that. So programs got to be tiny, and they must have everything in line, must do no function calls, and they must last long enough so as to absorb latency. So little loops, we have even this little, we made this even little song, all the funny little loops. Back in Guangzhou at VLDB, we even played this song. Ying, who spoke yesterday from IBM, even recorded it for us in Chinese. It's a nice little ditty, and there's profound wisdom in it. So, okay. So how do you get minimal programs? Wave gets minimal programs by making them, by generating them. So the only instructions that you execute are actually instructions that have to do with manipulating the data. Vectorized interpretation is not very good on GPU, but is perfect for CPU. So libcudf, which is the grandfather of us all in the accelerator space, gets little loops by using cab and thrust and things like that, where these, which are like building blocks, and then it does lots of round trips for scheduling these building blocks on device. But the advantage is that these building blocks are tested and pre-compiled, and so you're kind of less vulnerable to compiler errors and stuff like that. Compiler errors, by the way, exist. I mean, on CPU, we don't see that very often. On GPU, they are more frequent. OK. So the expertise is scarce. Nobody knows how to program that stuff. So there are some approaches to that, like the Triton language from OpenAI, but it might still not be perfect. The intuitions that we think we understand from our experience on CPU is hit and miss on GPU. It's just as likely not to apply. So, and then even though a lot of it is written, everything that's written about GPU is written about performance, because that's the only reason you run a thing like that. So even so, there's no replacement for trying it yourself. You got to understand these loops by writing them. You cannot read about them. Even though NVIDIA has a meritorious number of blogs and stuff like that that are helpful, it's no replacement for doing it yourself. You need to get to the metal and see how it works. OK. So vectorized interpretation, what we do in Velox all the time is basically we decide for a little bit what loop we're going to run. Then we run a loop for a real long time, a loop per array. Then we decide next loop, next array, next loop, and so on. And it works great. The time to decide is very short, and the time in the array is long. And the time in the array is well spent because you have out-of-order execution and instruction-level parallelism and all these prefetches and stuff like that that CPUs are built for. If you try, we broke our heads trying to do vectorized interpretation on GPU. It doesn't really work because the loops are short, and the loops side-by-side lanes or to address side-by-side memory, and this doesn't really work out. We tried and decided that it's not a good direction, so we pivoted to code genning and think that this is like a future-proof approach to that. OK, so next. So code patterns. See these actual little loops that are so funny, and sometimes they do this and sometimes that, and then sometimes they do something else. These loops are of 5 main types. There's table scan, and proxy for table scan is prefix sum, so filters, counting nulls, all of that stuff is like prefix sum, which is the #1 basic algorithm. The first thing you learn about GPUs is prefix sum. So this is table scan. Expressions is basically you just do the same thing on side-by-side lanes, side-by-side values. So that would be the kind of best thing that GPU is built for, except that you have nested data, and sometimes you have 1,000 elements inside the array for one array. So if you have things that run at very different width, you should do that in different kernels at different widths, and then you should adapt based on that. So that's a pattern of adaptivity to data size. What algorithm you use depends on how much data you run through it. OK, then there's group by. Group by is a hash-based operation that runs out of memory all the time. So you have to pre-allocate things, and remember, no memory allocation on device. So you have atomics, but that's all the memory allocation you practically have. So then it means that you have to have synchronization between host and device to provision more memory while you do this cache missing, constant cache missing stuff for updating the accumulators. Then the other part, the hash join is another pattern. So hash join is just like a random access followed by reduction. Now, if you're lucky, it's all that it is. If you're unlucky, you have one-to-n join where you produce multiple rows of matches for one input, and then you have to deal with that. So unnest is the same thing. So that's another kind of little loop. So repartition is the final little loop that just splits things into other streams, and we'll see. So out of these little loops, we have done everything except repartition in Wave, and so we have an instance of all these patterns. We got to get the pattern right, and then we can broaden it, but there's little point broadening it until you have the pattern right. OK. So then the basic execution model that we have is we generate a couple of kernels per query fragment, so typically one for table scan and one for everything else. Or if it's an inside fragment that starts with exchange, and the exchange is part of the fragment, and if you're lucky and you don't have too much cardinality variation, like big nested arrays or stuff like that, then you can just have a single kernel. If you have, let's say, 20,000 columns, then you want to do 20,000 columns in parallel, each in its own block. And then you have a couple more kernels. But very few kernels per query fragment is the idea. And then you launch them all you queue them up, you don't wait for results, you just, there are very few cases where you want to actually launch something, read the result, decide based on that, and then launch something else. Sometimes when you have variable length data, you must do that, but that's to be avoided because that's a full synchronous round trip, and synchronous round trips will kill you. Okay, so, okay, the grid. So run few queries because you don't have as much space on the device, so that you got to get low numbers of queries running very fast. You cannot, or should not, expect good utilization from having lots of queries. And so it means that you have less contention for space, less space for hash table, less space for buffers. But then it means that you must extract these hundreds of thousands of threads of parallelism from a single query, meaning that you do all the columns at the same time, you do relatively large batches, you just extract all the implied and explicit parallelism you can. Okay. So then what's called a wave in GPU language is a full wave is when you launch a kernel that will occupy all the compute units available on the device, and then if the width is a multiple of that, then you have multiple full waves, and then you should kind of configure the compute so that you can saturate the device with a single stream of control. Now in practice that's not possible because not everything has equal width. But maybe with a couple of threads of control, so a couple of independently proceeding files of one query or a couple of queries, you could get full utilization. That would be the target. So you want to shape your compute so that it fits the shape of the device. Okay. So have we now solved the problem? Well, if TPCH was the only thing we were doing, we almost would have, but reality is quite different. So the long tail, is it going to have you? So what we see, of course, I'm a great fan of TPCH. I wrote a very extensive blog series over a decade ago saying everything that can be said pretty much about query optimization and execution for TPCH. But then, surprise, none of the challenges that we find in Velox on the field are predicted by these benchmarks. So of course we design for the benchmarks, but what we find is that the challenges are quite unpredictable and different from the benchmark ones. So the benchmarks, of course, are not entirely without value because they do provide a checklist for the common operations that also exist in nature. However, the data sizes are different, the mixes are different, and the trick questions that are implied by the benchmarks are often not the trick questions that reality poses to you. And so it is true that these main operators that the benchmarks consist of, table scan, hash join, and group by, and repartition, are together maybe 85% of presto batch CPU utilization. However, the development work, 90% of that goes into functions, goes into corner case behaviors, goes into resource allocation, resource management, resource contention, things like that. And the benchmarks don't prepare you for that. So the long tail is quite different from the, you know, the 80-20 thing that the benchmarks target. Okay, so accelerators, for example, the NeuroBlade proposition with Velox is to just take table scan and hash join fused with table scan and filters and a couple of expressions, and because that is quite large, that's about half the work, and if you do half the work in a tenth of the time, then you can get an acceleration like NeuroBlade reports of 2.5 times by using their accelerator for just these specialized functions. But it's hard to get beyond that, and for us to have a really compelling proposition, we should at least get a multiplier of 5 on everything, with a multiplier of cost of maybe 1.5, so 3x efficiency in total cost of ownership. Something like that would be like a triggering condition for us to have the next-gen data center with accelerator first. So we need to do more than just accelerate the obviously acceleratable things. So then this brings us to the topic I've addressed in private with lots of my fellow accelerator cats. like, can we have a shared effort for building up the long tail? So that I'm inviting everybody who's into this space after the panel to a meeting where we can discuss these specifics of how are we going to come together and under what circumstances that would be beneficial. Okay, so benchmarks. Benchmarks are, of course, if you look at history where potential competitors cooperate, they cooperate in benchmarks and standards. So you could look at benchmarks. It's obvious why everybody wants benchmarks. A benchmark is the beginning of marketing. And of course, these standards are then the interop that makes a comparability and sometimes will also like cause to be actually a source of resource sharing. So we have done some work with Intel inspired by the AI training workloads that Masha was talking about. So this is the feature engineering benchmark. You can find it on GitHub. It's not complete. It takes the TPCDS warehouse, and then it adds as an event stream, so clicks and ad exposures, impressions, conversions, e-commerce type activity, and then you build a recommender system training set from this synthetic data. And that's more like what we do than the TPC ones. So it would be a step in the right direction, we believe, but it requires a community to work on it, and right now it's kind of halfway there, but not entirely. Okay, so composability finally. Composability is a big Velox thing, obviously, and composability in principle, if you think that GPUs is no memory management on device, and it's only pointers and arrays, the ABIs or agreeing on ABIs, application binary interfaces, on a thing like that should not be too difficult. So there is some hope for composable components that would come from these many like streams of GPU accelerated developments. We'll have to work at it and make something happen there. Okay, so adoption. Again, adoption is universal in AI, moderate at the very beginning for data management. So no code portability. Expertise is also not very portable. You need back-for-back compatibility to migrate systems. So we had a ton of work. Most of the work in deploying, let's say, Prestissimo in the place of Presto was about addressing long tail and compatibility and application idiosyncratic behaviors like regexps and stuff like that. So then the other thing is that the very most expensive GPUs go to relatively price-insensitive applications, and data management in bulk is not price-insensitive. So the top-of-line models, pricing-wise, don't really make sense. So we have to have like a mid-range GPU where we get great price performance, but then we need a data center that's built just for that. And before somebody builds a data center just for that, the software has to be mature, and they have to be convinced that the software is going to do everything. Because if all you got is GPU, then the GPU is going to have to do all the work too. So, but on the other hand, the good news is that public clouds are offering this kind of capability. So Meta would not be running its data centers in a public cloud, but many others will, so smaller applications can migrate maybe sooner and provide like this proof of viability. So now to the application. So the evolving workload means that new things, fashion is cyclic. I mean, the things that were trendy back in the day may come back, and so is the case in physical design. For a while, when Presto and Spark were created, it looked like physical design was gone out of style. It was like some dinosaurs maybe knew about it, but it was no longer relevant because in the age of big data, we have like four things that we do. It's full scan, and then we do hash join, and then we do repartition, and then we do group by. And if these are the only operations that we do, and I mean, we can implement all these benchmarks with these operations, then life is relatively simple and query optimization is quite straightforward, and there's not very many cliffs unless you screw up in some radical way in these. So you have like a space with a relatively cliff-free, and everything is equally slow, and everything is tractable once you learn to think in terms of these operations. But it turns out that reality has progressed since these days, and the big applications that we see very much depend on physical design. For example, data orders, doing index lookups even, who would have thought? But index lookups is a reality on the floor, like Masha was talking about. So co-partitioning, all the physical design stuff, it has come back to us. Plus, of course, that we need to extract more parallelism, so then we cannot expect large numbers of queries to give us the utilization. We must break queries into more and more threads, meaning that we have to do these columns, let's say, in parallel. So intra-query fragment parallelism in new ways. And then we need to have optimizers language technology that can do that sort of stuff. That was not anticipated when the Presto and Spark optimizers were built. Okay. So then the present state of the art, let's say Calcite and Presto and Spark Catalyst, they do a fairly okay job if all you got is these operations, a full table scan and some filters and some repartition and hash join and group by. They kind of know how to do that. And even then, they're not brilliant, like as evidenced by IBM's use of the DB2 optimizer as a service. So one incentive for us to look into that was if we wanted to do perfect benchmarks, then we would have to play an optimizer card, just like IBM did. But IBM had greater incentive to go in that direction than we had because we are a user and IBM is a vendor. So, okay, it's changing shape. So cost model, we will make this revolutionary statement. It has a fancy name. It's called epistemological realism. It means this weird belief that there is an observable reality out there and many people can look at the same thing and see more or less compatible interpretations. So in terms of cost models, reality first. So this means that whatever you build, when you build your plans, you build plan candidates that consist of physical operations, and if they consist of physical operations, then you have physical execution histories, and then you can even have correct cost model. Because just these statistics and these abstract formulas are wrong by a factor of 10 all the time, and quite justly nobody trusts them, and cost-based optimization has a bad name, but it does so only because the cost part is not controlled, and we can do that by sampling. If you expect to run a long query, you can fully well invest 1% of the running time into sampling in order to have a reliably good plan on one side, and then if you run the same thing all the time, then you already know the cost from history. So of course, shuffles are very important. Late materialization is going to be important because often we see like data shapes where there's very few columns that participate in joins or filters, they're the control columns, and then you have huge, like tens of thousands of columns that participate only in projections and other payload. So then you can figure out the selection and figure out the joins and figure out everything, and then only lastly will you load the vast bulk of the data. And if training is your consumer, then you probably want to load it directly into the GPU using GPU offload stuff like Wave or CUDF or other players in that space. So the shuffles are certainly key in deciding if a cost-based decision of does late materialization make sense, because the principal thing that you win from that is you don't have to shuffle data around. So shuffle is something that you have to cost. So physical cost model. Okay. So then composable QO, do we have the brazenness of saying that we're going to make a successor to Calcite? It seems that events and market pressures and our own observations are taking us in this direction. So we have had the VRAX originally like a private sport of mine, but now it's becoming a real thing. And this will be the Velox optimizer play. And we will find uses for it in the AI data preprocessing, and we'll find uses in interactive query, and then over time it will migrate in capability to rival the Presto and Spark optimizers, and like this there's going to be a broader stack of like Velox-based components to do big data. Okay, so So bringing it together. So we talked about language, we talked about accelerators, we talked about code-gen, we talked about vectorized interpretation. And when we have these things, even on a CPU target, if you have these data frames that have 20,000 expressions, they are not necessarily the best target for vectorized interpretation. So there is a point to maybe code-genning these things. And if we have code-genning into C++ in Wave, then we could deploy that there. And if we have intra-column parallelism in the optimizer, and of course we have need for intra-column parallelism on the GPU, and we would have need for that on the CPU as well, then we would see a future where many things would go to compilation, including these big data frames that pre-process data for training. And then we would get, well, it is a typically long running, so you don't worry about compilation times. Okay, so so then the other thing is, like I already said, we unlock efficiency by looking at the whole holistic value chain from table scan to all the transformations and joins and enrichment and what have you, denormalization, all the way to training. You see training as an aggregate, and you see inference as a UDF, and this is your AI-first data world. And now to do query optimization in that space, you have to have your own capability to do that, because you don't necessarily want to shoehorn that into existing things, such as the Spark one or the Presto one, because they will confine you to a single platform, and then you'll have to fight every step of the way to make these things accepted by whoever is maintaining these things. So then the situation is like people like to own their own area, so that's why black boxes get made. And now there's a few black boxes that will have to get unmade, simply because it's not practical to have, let's say, full dataset materialization for each training job. Rather, you would repurpose the data, make different feature selections, different data cooking, different this, different that, different enrichment for different models based on common data, and that's already happening. But we just need to break a few more black boxes to make it more efficient and to use Velox as a fungible execution way so that we can run on CPU, GPU, what have you, including maybe our own silicon at some point in time. Notably, PyTorch has gone into compilation. They use OpenAI's Triton as a target. It's conceivable that Wave could generate Triton as well, and then it could be like co-resident with PyTorch. It's not our first choice, because if we go to this great trouble of going to GPU, then we like to know what's our kernel boundary, and we like to know where the barriers are, and we like to know where's the data transfer and where's the synchronization and stuff like that. But on the other hand, Triton, at least on the surface, appears to have lots of the low-level intrinsics that are proper to specific GPUs and stuff like that. So maybe we can express that stuff there too. So that's to be seen. Okay. So finally we come to our grateful realization that we're in great company, and that all these players in the accelerator space are in the room, and that we have a great opportunity to learn stuff and to do stuff, and not just to compete with each other, but to actually create a market and make this thing that is now nascent to be the mainstream of data management in so many years. So then there's practical things. We can address the long tail. We can create benchmarks. We can create transparencies in this domain. Everybody says 10x or 5x or whatever x. But these claims are not comparable in and of themselves, so maybe we could have players produce runnable, let's say, Amazon images or something like that, and then agree on benchmarks and agree on measurement and create transparency in how this stuff actually works so that people can play with it. For example, this PyVelox is a step in that direction. It would make things very easily experimentable, and insofar we have at least CuDF and we have Wave to execute Velox plans, then one could just do hands-on GPU evaluation using techniques like that. It's not very far away, so we'll get there. And then of course Velox is kind of a nice starting point, because Velox has a lot of semantics that are in place, and Velox has lots of tests that verify this semantics. So developing this kind of convergence inside the Velox ecosystem makes sense just by virtue of this large coverage and a good community and a really wide and significant industry adoption. So I'll leave you with these thoughts and see you at the panel and then the meeting after that. Thank you.
Thank you, Ori. Are there any questions while we wait for our next presenters to get ready? Oh, okay, there are a few questions. Hold on.
That was an interesting talk, so thank you. But I wanted to focus just on one, perhaps on the performance aspect. If you could tell the compute vendors, like, what's your ideal cache line size based on, your observation of all the workloads and things like that. CPUs, we have 64 bytes, but maybe that's not the right size for the things you're thinking about with respect to large loops and little, inner loops. Do you have an answer for them? Like, what your preferred cache line size would be, given the workloads you've observed?
Cache line. Okay, so 64 on CPU seems to be universal. We don't know of anything better, and we are not sure that better exists there. GPUs tend to have 128, and then they have these sectors, so you don't necessarily load all the 128. I think that's kind of good. Would it be that you'd have a 32-byte line? I can't say. I mean, we miss the cache all the time. So maybe if you had so if you read 32 and you reserve 128, then that might be suboptimal because it's going to give you low hit rate because the cache is going to be all over the place. The places where you need cache is when you have scattered access patterns such as a hash join or group by or stuff like that. And there, it seems to, this sectored cache that we see on GPU seems to decrease the hit rate, but then GPU is not counting on the hit rate to begin with so much. So that's a good question. We don't have an answer, but I think we can work with the stuff as it is, and maybe more experience will give us more insight.
Thank you.
So my understanding is that both Velox and Glutton can use GPU for acceleration. But have you done any performance comparison between the two?
Well, we have, of course, well, let's say our take on that. Okay, if we just to give a data point, if we have, let's say, table scan and aggregation and filters and expressions, and we're running on a Amazon G5 with an NVIDIA A10 and a 16-core EPIC, we have a multiplier between 4.5 and to 6.5. So that's one data point. But it's not the data point on which you would hang the fate of the world, because these multipliers will depend on your choice of CPU and GPU and so on. So the multiplier on either side of 5 is commonly cited and also observed by us. Now, to what degree are Presto and Spark GPU acceleratable? It depends on the maturity of these things. So out of these plays, libcudf is the most functional, and then Wave is kind of the next-gen challenger to libcudf, if you like, but it's not as functional as yet. So we don't really have... Rivos, for example, did some studies with rapids, and they got some numbers. So we have a solid demonstration that there's high multipliers in the game, but right now our focus is to get the engineering principles right and the paradigms right and the, parallelizing the compute and optimizing the compute, not doing extra work, scheduling the work right, and having all the principles in place, and then the multipliers will come out of that. So I would refer you to the study by Rivos. I don't know if they'll be talking today also. Maybe they can say something more concrete about rapids. And of course, to NVIDIA is going to talk about libcuDF in Velox, and as these things become more available and more ready to use and more transparent in terms of their performance, because you can just go and try them, then these questions will solve themselves. But right now there is like industry-wide belief and investment in the fact that there are like large multipliers and there are no other sources of large multipliers. So an accelerator game is the game if we are going for, let's say, a 5x on top of what we have now. The proven reserves, if you like, of performance optimization in Velox are under 10%. So if we did every CPU trick we knew, we could get an across-the-board other 10%, but not much more than that. So you want to go farther than that, you got to go special architectures.
Thank you, Ori. Appreciate it. All right. Yep. Clap. All right. I'll introduce our next presenters as they get set up. So we have Greg and Karthikeyan, both from NVIDIA, who are going to be talking more today about the work they're doing accelerating Velox with Rapids QDF.
All right, great guys. Thank you so much for having us today. I'm really excited to talk about the progress that we've made working with Velox and QDF. I'm Greg Kimball. I'm the lead for QDF from NVIDIA. I'm going to give some kind of an introduction and set some context, and then hand it over to Karthikeyan, who's with me today. And a few other folks on the team, Dave Everett, Bradley Hasib, contributed really significantly to this. But really appreciate the time to get to share some of the work that we've been doing. So yeah, I'll do the first section, just talking about kind of how we think about Velox from the QDF perspective, and then I'll hand off the rest for Karthikeyan to walk through. So yeah, we really love Velox. This is a great community. This is a great conference. Thank you so much for having us. And we've, you know, yeah. We are just huge fans, and you know, the open source part of the community is just really important to us. It makes it so easy to get started and learn more about it and get support along the way, like the code review process, the careful CI work, really critical stuff, and it's just so great. We love it. Being a C++ execution engine, I mean, Velox is a really unique thing. There's nothing else like it out there. And part of it is just what it is, also with the pluggability and customizability. If you're looking at other engines and other data processing tools out there, they don't have the commitment to extensibility that Velox has, which made it really an interesting target for us to try to integrate GPU compute into it. Also, the good separation between execution and operators. There's a good separation of concerns. You can do operator replacement and still have it run through the same engine. That's another really powerful thing that not every engine makes easy. But really the big thing is the communities. The Spark, Gluten, Presto, C++ community, there's really nothing like it. I mean, any one of these bullets, Velox is unique, and then all together it's just it's a revolution. It's a great product. And the migration work from the Presto C++ talks in particular, you know, from Uber and Pinterest and within Meta, this is huge progress just in the last year. So, you know, congratulations to all that. One thing we really love about Velox is also the goal of being unified, not just a query engine, but also AI workflows, also streaming data frame processing. You know, Velox wants to do all those things, and we really resonate with that from the QDF side. So if you aren't too aware of QDF, I want to give a kind of quick intro. You probably know everything I said on the last slide, but maybe there's some new things here. So QDF is also open source, CUDA C++ library. You can find us on GitHub under Rapids AI, and you know we've got Docker images, Conda packages, pip packages you can play with. Spark Rapids jar uses QDF. It should be easy. We want it to be easy to get started. So. libcuDF is the core here, the CUDA C++ core, the library for CUDA data frames. That's kind of what QDF stands for. We're Arrow compatible. It makes it really easy to do interoperability with Velox and other tools that use Arrow with the cuDF column and table data structures. And cuDF is all about really efficient single node, single GPU algorithms. And from Ori's talk, you can see how maximizing GPU utilization is critical to having a good application. So that's what we are trying to do with every function call. Whenever you call the C++ API, we're trying to use the GPUs as best we can and get you, the data back with the lowest latency. cuDF we've gotten a lot of experience working with Spark Rapids, working with cuDF pandas and polars, and trying to serve each of these different conventions and different expectations that these libraries have. So we kind of share that with Velox, where we don't want to just have one front end. We want to be able to serve any front end. And I was trying to think of a good way to talk about what's in libcuDF. So what I did here is I took the libcudf.so and just took out all the function signatures in the public API and gave them a box, and then kind of put boxes around the boxes. So each box is an API that you can call. That's a really well-tested thing, probably used in Spark Rapids. And you can see there's a big focus on I/O, doing efficient parquet, orc, JSON, CSV, data processing, compression, decompression on the device. We've also invested a lot in strings and list and struct support because it's great to do integers and floats quickly, but a lot of the data out there requires a lot more complexity. And then relational algebra, aggregation, sorting, stream compaction, joins, nulls handling. These are all areas that we've had to really get into the weeds with Spark Rapids and other communities. And I really appreciate the long tail discussion about UDFs. And we have a JIT module I want to highlight at the bottom here. This lets you take C++ code or send PTX directly into a libcuDF function call and apply it to your Arrow data. So we have some infrastructure for this, and we really want to explore that long tail and make sure we can do that work, grow this infrastructure to support that. Today I want to talk mostly, Karthikeyan is going to talk mostly about the Velox-cuDF integration here. So just to maybe say a little bit about the ecosystem where cuDF exists today. Spark Rapids is a great tool, and it kind of came up during Abhishek's talk from Google about dataproc. When he talks about Spark on GPU, he's talking about Spark Rapids under the hood, actually. So it hasn't. Spark Rapids is a pretty mature tool and a really great thing for future work with Gluten and Velox, because we kind of already know what, we have a really good benchmark in what Spark Rapids is doing. If we can't run cuDF with Velox better than how Spark Rapids can run cuDF, we've got a performance opportunity, and we know we can really study that in detail with profiles. So it's going to be a really great benchmark for us to work off of, is how does Spark Rapids do the same work. Spark Rapids is a Java Scala execution engine, and one thing that Velox gives us is a native execution engine. And we have some internal projects that do that, and it's been of interest for a long time, but Velox is by far the most productive and mature tool to bring that to cuDF. So we're really, really excited about it. The Spark Rapids comparison is really important. And going to native, we think that we should be able to get some benefits from not having to deal with the JVM garbage collection. Looking at AI workflows, there may be some cases where Spark Rapids has a bit-for-bit Spark compatibility guarantee. There may be some places where it costs performance to do that, and it's worth relaxing that for some workflows. The last thing is that having a good fallback, the CPU fallback with the Velox execution engine is right there at your fingertips, and is going to be much better than what Spark Rapids has to do today with column to row and row to column conversion. So I think this Velox-cuDF has a really great performance story ahead of it. But let's talk about what it is. Go for it, Karthikeyan.
I'll be talking about the design of Velox-cuDF and performance comparison. So we have most of the design of Velox-cuDF extension done, and we'd like your help to make it expand it and then harden it for production. And I'll be talking about design of Velox-cuDF extension and how we design the supported operators like order by, conversion, table scan and hash join, and we'll see how we can add new operators to the Velox-cuDF. To put simply, Velox-cuDF actually replaces the CPU operators in the Velox pipelines with GPU operators, allowing end-to-end GPU processing of query plans. So when a coordinator like Spark and Presto pushes query plans to Velox, the local planner in Velox decomposes that into individual pipelines and of operators. And drivers pick up these operators and run them on CPU. What Velox-cuDF does is the driver adapter replaces those CPU operators with GPU versions before executing them. So all you have to do in your application is call register cuDF, and the cuDF adapter will take care of the rest. When you call register cuDF, it adds a driver adapter, which takes care of the operator conversion. And it does a bridge translator that is used for joins. And it creates a GPU memory resource that is used for memory allocation. Let's look at order by. The order by and conversion operator support is already merged into Velox. A big thanks to Devrat Makar and Bin Cheng, who actually made this into Velox. So when CPU operator is replaced, the cuDF adapter adds conversion operator, which transfers the data from the CPU to GPU as a cuDF vector, and a GPU execution operator, cuDF order by, which calls cuDF C++ APIs to run the workload on GPU. cuDF vector actually is a data structure that holds the data in the GPU. The data is held in GPU as long as the upstream and then downstream operators are executed in GPU. If there are any operators that is running on CPU, the conversion operators takes care of moving the data back to the CPU if needed. The cuDF order by operator is a non-streaming operator. So it collects all the batches, concatenates them, and then calls C++ cuDF APIs to sort them. And then it packs the results back into cuDF vector object and then passes on to the next operator. The concatenate step is needed, but it's not taking much of time for TPC benchmarks like scale factors less than thousands. Now, let's look at the conversion operator. So cuDF vector is derived from Velox row vector, so that we give the same interface to the Velox's operators. And it has two components. One is cuDF table and a stream. Both cuDF table and Velox row vector have the same arrow compatible layout. Both of them support numeric types, string types, timestamp, duration, and dictionary types, and nested types like lists and structs. The interop APIs in both Velox and the interop APIs in cuDF allow efficient conversion, often requiring mostly only device memory copies. And the stream is managed by a stream pool. For the batch size between CPU and GPU will be different because GPU needs enough data to keep the GPU busy. So typically, the batch size will be in the range of either 100,000 rows or like a collection of like 1 GB of data. So besides converting data from the CPU to the GPU, we can start creating the batches in the GPU itself using table scan. So table scan can read local parquet files using parquet data source, and the parquet data source it can run the decoding, the decompression, decoding, and filtering are all executed in GPU, and it adds a stream to the cuDF vector from the stream pool for each split. So when this cuDF vector is again transformed using any other operators, it uses the same stream to run on the GPU, and the same stream is again copied back to the output vector. So the stream travels with the data, so we don't have to manage stream explicitly. And this parquet data source works with local files. Additional data sources like iceberg or remote objects or delta lake, these are not scoped yet, and we would really like help from community to add them. Next is hash join. So Velox's hash build and then hash port are in independent pipelines, so they communicate between them using an object called bridge. Similarly, in Velox-cuDF, it uses a custom bridge. So what Velox build operator does is it collects all the batches, concatenates them, and creates a cuDF hash join object and stores them in the bridge. Now, hash probe can access this bridge and call cuDF APIs on the probe input batches, and then produce the output as a streaming operator. Now, besides these operators, we have aggregation operators, filter project, and local partition, and more operators that can enable us to run the TPCH benchmark. The expressions are supported by cuDF expressions, and this expression can be expanded with adding new libcuDF function features and functions and binary ops, and also you will be able to run transforms with with user-defined functions. The number of drivers that is typically good enough to keep the GPU busy is around 4 to 8. So the hyperparameters that you need to configure is one is the batch size, another is the number of drivers for a single GPU. We'll see how to add new operators. To add new operators, Velox actually you need to touch only 3 functions. One is add input, another is no more input, another one is get output. Add input queues all the input batches, and no more input concatenates them if needed. For non-streaming operators like order by, hash build, and final aggregation, you have to concatenate them. For other operators, you can process them batch by batch. For get output, it takes the concatenated table or each batch and then calls C++ cuDF APIs on the table and the stream that is available in the cuDF vector, and then gets the results and then packs them back into cuDF vector and then passes on to the next operator. So this kind of modular designs allows easy extension of libcuDF features into Velox, and we would like developers to add more and more operators into Velox-cuDF. Next, we'll see how the performance comparison with CPU. So for performance comparison, we ran TPCH benchmarks on scale factor 100 on different systems. On the left side, on the right side, if you see, we ran Velox on a 32 drivers with 32 drivers on a 32 core physical core system. It took around 134 seconds. And on the same system with L4 GPU, it was able to run at 44 seconds with 2 drivers, giving a 3x speed up. And when it's run on Grace Hopper Superchip GH200, with 72 drivers, with 72 physical cores, it was able to run at 92.5 seconds. But on the same H100 GPU in the Grace Hopper system, it was able to run at 12.8 seconds, giving a 7.2x speed up. And this for the GPU, it was run with 8 drivers. Now, this is the splitter for each individual queries for the speed up. The Q4 probably has a performance issue in Velox because this abnormal speed up is due to a recent bug. But all the other queries, if you see, the speed up ranges from 10x to 3x, except a few outliers. Okay, so Insight Systems is actually a great way to visualize how GPU is utilized, and to see actually how different components of the GPU is being utilized. The main things are actually the compute, the GPU memory bandwidth, and the data transfer between CPU and GPU. So first 3 rows in this profile shows that how SMs are used, SM active, warp active, and then warp inactive. And the next 2 rows, DRAM shows that is GPU memory bandwidth. And the next 2 rows shows the bandwidth from CPU to GPU. Then the last 2 rows shows the kernel execution along with memory operations. So Velox-cuDF has a very good compute utilization and also GPU memory bandwidth utilization and PCI Express bandwidth utilization. So this is a profile for query 12 on a scale factor 100 with 2 drivers on L4 GPU. All the queries start with table scan, so it will start with copying the parquet files from the host to the GPU. So it starts with PC Express read, and it will wait until once the PC Express read for the one thread is done, the kernels will start. But the second layer will still continue the PC Express copy, doing a simultaneous memory copy and kernel execution. Once that's done, the second thread also will start executing the kernels. So we'll have concurrent kernel executions at the same time. So that gives us a very good GPU compute utilization. So if you see the warp actives are mostly at the high. And memory bandwidth, it depends on actually the kernels that run on the GPU. So most of the kernels are actually initially will be decompression, then decoding, and then some other operators like aggregations and hash joins. To not run out of memory for all the queries, we have to choose batch size that is like small but still big enough to keep the GPU busy. So for L4 GPU, the 1 GB batch size is good enough so that all the queries for scale factor 100 runs without out of memory. Next, we can see what is the work breakdown and the whole TPCH benchmark on the scale factor 100. In the TPCH benchmark, it is mostly the 85% of the time is taken by table scan due to the high throughput joins and aggregations. If you look at the overall breakdown, the I/O part, which copies the files from the OS cache to the CPU and then to the GPU, takes around 24% of the time. And the decompression of the parquet pages in the GPU takes around 26% of the time. And the decode part, which actually does dictionary and run length encoding, decoding, and creating the parquet, decoding the parquet data and then creating CUDF columns, takes around 35% of the time. The other operations like join aggregation run at high throughput, so it takes around, most of them takes around 5%. And there are other operations like cache and concatenation, which are very negligible, which are not even shown in the graph. If you look at individual queries, most of the queries are I/O dominated, except query 13, where the joins and aggregations is run on a very large data, so that is significant. But generally, in all the TPCH queries, it's mostly I/O bounded. Okay. So Velox-cuDF is a pure C++ library, and you don't need CUDA experience to get started. So all you have to do is refer the documentation of libcuDF, and you will be able to find most of the functions that is required for GPU data processing. So in Velox public repo, we have a storyboard issue, which contains steps to how to build and how to run and then how to test Velox-cuDF. And we have the first PR on the order by and then the convention operators already merged. We have our fork with the support for other operators for running all the TPCH benchmarks. So we'll really appreciate the community's reviews to while upstreaming these operators into Velox. The Velox-cuDF is checked into Velox experimental cuDF, and this Velox-cuDF brings like great performance and GPU compute to Velox. And right now, Velox-cuDF is able to support TPCH benchmarks, which only a fraction of cuDF APIs. There is a lot more function that are available in libcuDF that can be ported to Velox. And if you are without using libcuDF, if you want to write your own kernel for certain operations, you can do so because the cuDF actually offers a zero copy interop via arrow. So you'll be able to access the same data that is available in the libcuDF data structures, and you can write your own kernel to do custom operations. And to set next targets, we need community's help. We have big thanks to Bin Cheng, who actually helped with adding gluten support and then testing the order by and conversion operators on the GPU. And we expect we'll need support for spilling, for like host spilling from GPU to CPU, and exchange operators and additional connectors for table scan and more. That's all. Thank you so much. Thank you, Velox team. Thank you, community.
So I got really two questions. So first, number one, so you did the TPCH benchmark. So how many GPUs are you attaching to a given hardware box?
One.
So, and then you did at the scale of 100?
100.
So realize that for a given hardware box, we are running comfortably at the 5,000 to 10,000. So I don't know what this means.
You mean scale factor 5,000 to
Correct.
10,000?
For a
Okay,
single
so
box of a regular
Yes.
box that you get from Amazon or whatever.
Okay, so the scale factor 1,000, the 100 is actually tested for our L4 GPU, which has like 24 GB memory. But we were able to run scale factor 1,000 on a H100 system, except 3 queries which are actually running out of memory.
But still you're off, because on that side I'm doing 5,000 and 10,000. So that means that I have to put 10 of these GPUs or 5 of these GPUs over there.
Yes.
Which
right
makes it
now,
very expensive, right?
Yes. If you look at so right now the Velox-cuDF doesn't have certain features like dynamic filters and exchange operators. Once we add them, the speed up will be much more. But we'll be able to scale better.
Yeah, okay, so that's future work.
Yes.
So the second question that I have is that the batch size, how did you decide on that one when you have aggregate functions? So you don't know really the working memory of the hash table because it depends how much compression you're going to get on your group by columns.
Okay.
So what do you do when you bring a batch and then it just doesn't fit? Because the hash table is just too big.
Right now, we do break as out of memory. But I think when we add spilling support, we'll be able to move some batches which are in the GPU memory to the host memory, spill to the host memory. So we'll be able to do that part later.
So you do it yourself, or you have to go to Velox to help you on that?
It will be part of the operator, actually. Operator.
Okay, so you offload it back to the CPU, and then you
Yes.
bring back and do the
It'll
rest.
be a spilling manager that will be
Okay, so you chunk it,
operators.
which going to cost, by the way, every time you
Yes.
do that. The round trips are very expensive. So it's important to measure that, because often we hit that thing, it's just called the spilling, you know, so.
Yes, spilling is totally.
So you have to take care of the cases that you do spilling and measure that.
Okay.
Okay.
Okay. Thank you. Awesome. Who's left? Okay, so next I'm going to have David come up from Revos, who's going to be talking about Breeze and Wave, multi-architecture acceleration for Velox.
Great. All right. Hello, everyone. My name is David Riverman. I'm a software engineer at Revos. Revos is a hardware startup based in Santa Clara. And today I'm going to talk about the work that we've been doing with the Velox team to enable acceleration on the hardware that we're building using Wave. So here's the short agenda. First, I'm going to talk about something called Breeze and tell you a little bit about what that is and how it's being used by Velox Wave. And then give you an update on the current status of how the integration into Wave, and then a little bit about what's coming next. So what is Breeze? So Breeze is really it's a header-only library providing SIMT acceleration for data analytics algorithms. So originally, this was developed internally at Revos to help us with our hardware design and to understand how to, build the right hardware for accelerating data analytics. And by working together with the Velox team, we decided to open source this code. So it's the initial part of the code is now living in the Velox repo, and you can find it in the experimental folder. It's So it provides a portable implementation of a bunch of building blocks for data analytics. So it's portable across both APIs as well as architectures. So it means it's not limited to CUDA. It will also work with HIP, SYCL, and OpenCL. And it's not making a lot of assumptions about the architecture that it's running on. So for example, it might not make any specific assumptions about like register file size or shared memory. It tries to be pretty flexible there so that it will scale well to multiple architectures. There is a mechanism in there to support vendor and architecture specific specializations for optimal performance when that is necessary. So for example, sometimes you might want to reach for on NVIDIA hardware for some PTX code that is not available using the normal CUDA API. Then there is a mechanism to do that, or some other kind of compiler built in that you can't access using the standard API. So there is a mechanism to do that, and there's a proper abstraction, so the code keeps being portable. And it's kind of designed to easily integrate into existing projects. We want it to be as simple as possible to use this in existing code. So you kind of just want to be able to copy a header, put it in your project, include it, and use it, and that it should be as simple as that. So in some ways, you can kind of think of it as, if you're familiar with a cub, you can think of it as a cub, but with a focus on data analytics and whatever the needs are for Velox Wave, and also being portable across APIs and architectures. So a little bit more about the design. So there's different API levels. Sort of at the lowest level, there's something called like a platform API, and that's where you can find some pretty basic things like things that might be different depending on the API you're using, such as how do you get your thread ID and special warp intrinsics and so on. You'll find that, and as a user of this library, you can decide just to use that to use that abstraction. On top of that abstraction, there's a large set of what we call like kind of block-wide functions that are built on top of the platform API. So you can use that. If you're familiar with cub, this is very similar, and similar to the sort of the block-wide functions in cub. And then on top of that, we also have an API level that we kind of refer to as algorithms. So that's basically a lot of these block-wide functions being combined into more complicated algorithms, like for example, radix sort or something like that. So those are sort of the levels, and you can kind of pick and choose what you want to use. And I'll in following slides I'll go through kind of what Wave is currently using, and that might change over time too. We have a really exhaustive set of correctness and performance tests for each of these levels. That's helped us design our hardware, of course, and it also makes it easier to get new architectures to be correct and perform well when using these functions. For the performance test, we actually have one more level beyond the algorithm, which we kind of refer to as queries, and that's basically taking the algorithm API and combining that into sort of higher level SQL queries. And that can be kind of used if you want to find out what the speed of light is for certain specific SQL queries. You have some hard coded queries there, so that's also in there. Another design decision is that we decided to keep all sort of policy and configuration external to Breeze. So we like all parameters that allow you to configure these functions, such as maybe the number of threads per thread block or the number of items per thread and those type of things. Those are all external. We don't make any assumptions internally in the library about what are ideal values. We basically allow you to provide them, and we have the performance test that allows you to do sweeps to determine what might be the ideal configuration for your specific piece of hardware. Okay, so what's the current status of integration into Wave? So we have been working with the Velox team to integrate with Wave, and right now we're using for some things we're using just a platform API. So these are basic things where you currently, if you want to do it in CUDA, you might have to reach for PTX or some other library that is less portable. So, for example, libc++ atomics with memory ordering and memory prefetching. So some of those things we get through the Breeze platform API, which allows us to specialize it for Revos hardware as needed. And then we're also using some of these block-wide functions today. So those are mostly kind of basic scans, reductions, and sorting. So it's pretty limited, but the exciting part is that this is enough for Velox Wave to now work with multiple hardware vendors and multiple architectures, because it's now running on Revos hardware in addition to NVIDIA hardware. Okay, so what is next? One thing we can do is we can, potentially add or migrate some of the existing Wave CUDA code into Breeze. Whether that makes sense or not might depend on different factors, but it would make some of that code more portable, and we would benefit from the correctness and performance testing that Breeze provides. So if you have some code that maybe needs tuning to perform really well across different architectures, that might be a good candidate for being moved into Breeze rather than living in the common Wave code. Like I mentioned, this is code that has been open sourced from Revos. There's a lot more code internally that we haven't open sourced yet, so we are planning to open source more of that, and it's probably going to be based on what is most useful for what we're doing in Wave and Velox. So we'll be working closely with the community to determine what is the most useful thing for us to open source. And obviously, if there's interest, we be very excited to potentially support more hardware vendors and more architectures. And given that Breeze already runs all the correctness tests and performance tests already run on with other vendors' hardware, we kind of create a path forward for doing that. It's relatively straightforward. Okay, so to summarize, Breeze is open source and it's part of Velox. It's how we enable Velox Wave to provide acceleration of Velox on multiple hardware architectures today. And it provides a robust set of correctness and performance tests that we can use for key software components in Velox that potentially use tuning. And it also provides a path for supporting more architectures and more vendors in the future, if desirable. And last, I want to thank the Velox community and the Velox team for working with us, especially Ori and Jimmy, who's been doing a lot of hard work reviewing our code. And and by the way, Revos is hiring. Thank you.
Could you talk a little bit about the extent of your the performance data that you expose? Is it just like wall clock time, or do you have a workbench that you can do experiments and garner other information about what's going on underneath for that are important for understanding performance?
I mean, the basic stuff is just wall clock time or whatever profiling that the specific API provides that you're running the test on. You probably have to reach for specific tools that the vendor provides if you want to do more deep dives into exactly what's going on. So we'll have, we have our tools, and obviously if you're testing this on NVIDIA hardware, you use their Nsight tools to get more details.
Okay, thank you.
Cool. Thanks, David. Okay, so we're in break now. So we have 20 minutes. We'll meet back here at 11:10, but feel free to go out, hang out, chat, and we'll see you back here in about 20 minutes. All right, we're going to get started. Cool. I am happy to introduce Meng from Meta, who today is going to be talking about Velox memory system improvements. Thank you, Meng. Go. You can use this for your clicker.
Okay, this.
Yeah, just try it to make sure.
Hello, everyone. So I'm Xiaoxuan from Meta. Today, I'm going to talk about the improvements we made to the Velox memory system in the past year to help the persistent migration. So here is what I will cover in this talk. We first discuss about the memory-related problems we encountered during the persistent migration, and then the key achievements that we made to addressing them. And then we next talk about take a quick overview of the Velox memory system to see how it works. Then we deep dive into the improvements we made in the three key areas, from performance, the query wound prevention, and the server wound prevention. So starting early last year, we are able to run most majority Presto batch query in Persistmo and see very good reduction in the CPU time savings. But unfortunately, we see the query wall time is much worse than compared with the Presto Java. And through analysis, we find out one of the main slowness is because of the slow memory abstraction. Then we heavily optimize the memory abstraction and the disk billing to fix the problem. And after that, Presto started migrating to a new hardware with much higher CPU concurrency and large measure memory capacity. And this lead to the CPU time regression compared with Presto Java. And through analysis, we discover the high lock contention from Velox own memory allocator is the main cause of the slowness. And we fix the problem by switching to JE-malloc-based memory allocator, which is better at handling high concurrent memory applications. And the second half of last year, we started deprecating LBM queries and migrating the QRT query to Persistmo. And this pushed our system limits. One main challenge is query running out of memory. And either due to that we lack of sufficient spill coverage for spill operators, or we see unexpected memory growth from the non-spill operators. So we extended the spill coverage for spill operator and built a memory mechanism to cap the memory usage from the non-spill operators' physical problems. And during the persistent migration process, we see the several wounds. Instance like either because the system is overloaded or some bad queries using excessive memory from non-Velox tracked memory system. It's like JE-malloc. So we built the generic memory pushback mechanism to handle the transient non-Velox tracked memory spikes. And in parallel, we keep improving the Velox stack to make sure all the significant memory allocation were made through Velox memory pool. And also for the non-Velox components, which are memory intensive, like the remote storage client we use in Meta, we built a throttle mechanism to prevent excessive memory usage when the client, either the client or the backend service in some unstable state. With this all improvement together, we significantly improved the reliability and the performance of the persistent running at Meta. Yeah, so next before we deep dive into the actual improvements, let's first take a brief look at how the Velox memory system works internally. So it makes up the 5 major components. The first component is the memory pool, which provides query memory allocation. So internally, it dedicates allocation to the memory allocator. It tracks the query's memory usage. The memory pool can dynamically grow its capacity by requesting more capacity from the memory abstraction through a process we call a memory abstraction process. The next component is the memory abstraction. The memory abstraction allocating capacity for the query and also abstract the memory capacity among them. So memory abstraction leverage the disk billing techniques to reclaim the used memory from the running queries if necessary. The next component is the data cache. And data cache provides an in-memory cache for the frequent access data. It doesn't allocate memories through. It allocates memories through the memory allocator directly, bypassing the memory abstraction and the memory pool, which means that the memory allocator needs to guarantee that the memory allocated to both query and the cache stay within a certain limit. The last component, when the memory allocator reaches the max capacity limit, it will shrink the cache to make the rooms for the new allocation. The last component is the memory pushback. It is the background daemon that runs periodically to check the system memory usage. Whenever system memory usage is go above some certain threshold, it will kick out the Velox memory reclaim process to handle spiky transient memory usage from the non-Velox components. That's how the overall Velox memory system works. The next I will talk about the performance improvements we made to Velox memory system. I think the one key issue we fixed is the slow query wartime problem caused by the slow memory abstraction process. So to understand the problem, let's assume that one query start arbitration. So all the other queries which requesting memory abstraction have to waiting for the current arbitration to run completion first, because we're using a single log to protect the arbitration process. So if a memory abstraction process triggers spilling, it can be very slow, because at Meta, we spill data remote storage, so which tail latency could be very large. By observation, we find out a small selected query, which takes like 10 megabytes of peak memory and finish in 10 seconds, sub-seconds is affected most. So if a small select query execution blocked by a slow memory abstraction process, its wartime can be slowed down by more than 100 times. So to mitigate the problem, we first added reserve a small percentage of memory capacity inside the arbiter to ensure each query has a minimum amount of memory to run. So this can help enable the small selected query to run through completion without interfering with the memory abstraction. But this doesn't fully address the problem. As for the medium-sized query, we still see significant regression in the query war times. So by observation, we realized that in persistable, most of the abstractions are local memory abstraction, which abstraction that only request reclaim the user memory from the requesting query itself, as it exceeds max capacity. So given that, we optimize this by parallelize the local abstraction execution. So we're using the read log for the local abstraction and only use the write log for global abstraction. So given the global abstraction, it rarely happens except the system is overloaded. So this largely solved the slow query wartime problems. And during this process, we also did a bunch of other optimization to make memory abstraction process more efficiently, like we will avoid excessive memory abstraction for concurrent requests from the same query. So before we start a new abstraction request, we will first to check whether the memory pool already has sufficient free capacity freed by the previous request, so that we don't have to start a new abstraction. And we also introduced the abstraction-aware driver yield control mechanism. So a driver will yield its execution if the associated query is under abstraction processing, so that we can avoid unnecessary blocking the driver threads. And we also did optimization to skip reclaim from the non-reclaimable query to avoid unnecessary task and pause and resume operations. So with all these improvements together, we effectively to solve the slow query wartime issues. To continue the memory abstraction optimizations, we redesigned the memory abstraction internally to further parallelize the global abstraction with local abstraction without a single lock. As we see in the diagram, when a query cannot allocate sufficient free capacity from abstraction, it will trigger the global abstraction by kicking out the background daemon called global abstraction controller to run. And the request itself just in the global abstraction waiting list. The global abstraction controller will manage the memory abstraction, memory reclaim process, like setting the reclaim target and also select the queries to candidate query to reclaim memory. To parallelize the memory claim from multiple queries, we introduce the memory claim executor. It is executed to do the actual reclaim from the query. When sufficient amount of memory has been reclaimed and returned back to free capacity pool, then the request waiting the global allocation waiting list can resume with the granted capacity growth. And if the memory claim process is running slow compared with the memory request demand, then the global abstraction controller will decide to abort the query to quickly free up the user memory. To ensure we have a class-wide consistency, the abort decision will consider the query age, so that the multiple workers will abort the same set of queries. We also optimize a lot about this splitting process itself to accelerate a single memory reclamation process. So we did the following optimizations. We first parallel the disk splitting processing across multi-layers. We support we support to parallel splitting from multiple operators from the same core in plan node. And within the same operator, we also parallel split processing by partition the split data. And within a table writer, we parallel the multiple files writer flash within the same Hive data sink. And we also optimize the disk I/O to reduce the split I/O cost to improve the performance. Like we apply the compression to reduce the disk I/O size. We also apply the write buffering to reduce the I/O processing cost within the remote storage client. And we also apply the read ahead on unspilled paths to pipeline the spill file read with the unspilled data processing to improve the spill queries latency. For sorted spill use case, we leverage the prefix sort optimization to accelerate the spill data processing. The next I'll talk about the optimization we made to the memory allocator to fix the CPU time regression that we see after Presto migrate to the hardware with higher CPU concurrency and larger memory capacity. Through analysis, we find out that this regression is caused by the high log contention from Velox's own memory allocator. And Velox's own memory allocator using a single log for space allocation so that it can strictly control the actual fixed memory allocation to avoid the memory fragmentation. But the problem that it could lead to the high log contention with increased allocation concurrency and larger managed memory space. To quickly solve the problem, we decided to switch to JE-malloc allocator, which has much better handling at high concurrent memory allocations. To mitigate the memory fragmentation issue potentially introduced by the JE-malloc, we rely on the memory pushback mechanism we built to handle to protect the server womb in some edge workloads. So next, I'll talk about the improvement made to the query womb prevention to help the LBM decryption and QRT migration to Persistimo. For those new workloads, we see some new we see the new womb patterns. Here I give some typical examples. Like for example, we see many queries in the hash join processing, and it is due to some edge cases. We don't have the spill coverage. For instance, there is a small time window that hash build has finished build a table, but before the hash probe start probe processing, and when memory abstraction trigger at this point, we cannot reclaim from either side because both are in non-reclaimable state. So to solve the problem, we added a spill trigger inside the hash join bridge. And early this year, we started migrating Sapphire to Persistimo, and we observed a new womb patterns that is due to pattern in the hash join. That is due to we don't have the spill support in the mixed mode execution. In the mixed mode group execution, the build side is ungroup executed, but probe side is group executed. To fix the problem, we are developing a solution to keep all the spill partition metadata inside the hash join bridge so that we can reuse the spilled build side data for cross multiple hash probe groups. We also did a lot of optimization, like fix the memory efficiency and data log fix around the parallel join build. So this enables us to run the hash join spill reliably and efficiently in production since the end of last year. The other common womb pattern we see both LBM and QRT is the table writer wombs. We do have a spill support for table writer, so by early stripe flush. But when those query wombs, each table writer has opened many files, and each file has only buffer a small amount of memory, so it doesn't reach the early stripe flush memory limit, so that the memory abstraction cannot reclaim memory from any of those table writer, even though each table writer could use up to gigabyte memory. This is already designed to parallel the table writer processing, but it's not a memory efficient. It can also cause many small files. And this only happens for the non-bucket partition table. The local exchange operator sit ahead of the writer pipeline will distribute the incoming data in the round-robin manners. So which means one table writer partition could be opened multiple times with one per each table writer thread. So we provide options for the user to fix this problem. So if configured, the local partition will partition incoming data using the table partition keys. So internally, the local exchange will maintain a map from the logical partition, table partition, to the table writer thread. Initially, each logical table partition only assigned to one table writer thread. During the query runnings, if we see high buffering in the local exchange and the total query capacity is within a certain limit, we will scale up the processing by assigning some hot logical partition to more than one table writer thread. So these kind of help to achieve dynamic balance between the writer memory efficiency and the writer CPU process efficiency. And also starting early this year when we see some new pattern in the Sapphire migration. So that is related to some queries with many stage. And the WOM happens right after the memory abstraction, local memory abstraction finish. And by observation, we find out the reclaimed memory capacity has quickly resumed by the running driver thread from the same query. Because for the query with large number of stages, it has a lot number of the driver threads running in parallel, so that to fix these timing-related WOM issues, we improved the memory abstraction process. Instead of to reclaim a fixed amount of memory, we fixed a certain percentage of the query capacity. This not only helps fix the WOMing problem, but also improve the memory reclaim efficiency for those large queries. For non-stable operators, one common pattern we observe in many different operators is we have inadequate output size control. The Velox driver execution framework has set output size limit, but initially many operators just respect the max number output rows, but they don't respect the actual output size. So we did a lot of optimization improvements, like for unset operator, hash aggregation, table scan, hash probe, and also extend the row container to provide faster row data size estimation to improve the accuracy of the hash probe output size control. And we also added row size estimation in nimble file reader to help prevent the WOMing for the table scan with nimble file format. The other common WOM pattern we found in the LBN and the QRT is due to the memory efficiency of the columnar page serializer used by the partition operator when dealing with wide shuffle, which has a large number of column streams. And we did a series of optimization from initial to optimize to support fine-grained allocation within the stream arena to avoid unused memory allocation within the Presto page serializer to eventually support the row-wise shuffle. This significantly reduced the peak memory usage of partition output operator. The other common WOM pattern we see in the table scan WOMs, that's due to the query just run too many table scan threads, and each table scan thread uses a significant amount of memory. To mitigate the problem, we provide option for user to scale up the table scan processing and a certain memory budget. With this all optimization together, we effectively to prevent the WOMs in persistent production and meta. So we will also continue to investigate and fix new WOM patterns when onboarding new query workload to Persistmo. The last time I talk about the memory pushback mechanism we built to handle the non-Velox tracked memory spike. And the memory pushback is implemented at a background daemon we call the proactive memory tracker. The proactive memory tracker will proactively track the system memory usage. So whenever the system memory usage go above some certain threshold, it will kick off the Velox memory reclaim process. It will first to reclaim the unused memory from the cache. And if it's not enough, it will go ahead to abort queries to free up the used memory quickly through the memory abstraction. And by adopting the memory pushback mechanism, plus the throttling mechanism we built for remote storage client, and the flow control mechanism we built for the HD-based shuffle together, we can effectively to handle the transient non-Velox tracked memory spike. Yeah. That's all I have today. Yeah, thank you.
We have time for like 1 or 2 questions.
Thank you. Is there any fairness process in when it comes to killing the query due to OOMs? Because I think you were showing that like if the query requests some memory, it would be killed like in some cases, but could it be the case when you have multiple queries that are, for instance, running, let's say, and using like 10 gigabytes, but there is another one which is just using 2 gigabytes, but it's requesting memory, but it cannot get it? will this query be killed, or some other offender, like or highest offender on the worker, will be killed?
Yeah, so when we abort a query, we consider the query age, but we actually have a certain threshold because we don't want to, kill some young queries which has a small amount of memories. We actually want first we see how much we have a threshold. We basically we put the query in multiple buckets based on the current memory capacity. Within the same bucket, we queue based on the age. For example, if the threshold, if we starting from, suppose like the query with 10 gigabyte memory is probably in the highest bucket, we first to abort from those queries. So we will choose those queries first, and then we go to if we cannot reclaim sufficient memory, we'll go to lower bucket to kill the 2 gigabyte memory. So it's most likely that we will first to kill the memory, the query with 10 gigabyte memory.
Thank you.
So you mentioned you're using JMalloc to do all the memory accounting now. Are you using internally the MM allocator for the memory or the malloc allocator? So JMalloc becomes more of a usage there, or how do you deal with linking just JMalloc into the final library?
So what's your question?
So you said you're using JMalloc to try to reduce the fragmentation and things like that, but
we're not using JMalloc to reduce fragmentation. We're using JMalloc for the high concurrent memory allocations. And to mitigate the problem, because the Velox own MM allocator is good at handle the memory fragmentation, and we are still using that for some internal directory queries, which are small queries. Use case. We're still using the JMalloc. We're still using the M allocator. But for the parallel batch, we are using the JMalloc because we are running on some high concurrent hardware platform to handle high concurrent allocation. So instead of optimizing our own memory allocator, we choose to using JMalloc to unblock the CPU time regression.
Okay.
Maybe time for one more. Pass it back. Oh, sorry, back.
Yeah, I actually also have a follow-up question for the JMalloc one. So you mentioned in one of the slides that when you have fragmentation, when you observe high fragmentation from JMalloc usage, you will apply pushback mechanism. Can you talk a little bit more? How are you doing that?
So basically, the pushback will check the system memory usage. If the system memory usage go above some certain threshold, then that's very likely the topper or the host will kill the process, right? So we need to free up the memory. So basically, we will kick in to reclaim memory from Velox. First, we reclaim memory from the cache, and then reclaim memory from through the mem abstraction, just abort the query to quickly reclaim the used memory. And also at the last, since we now using JMalloc, we also add to call release and dirty page from JMalloc. But very recently, we realized that that operation very expensive, could take like a minute in some worst case. So the pushback basically free up the memory back to the system. And so.
All right, I'm going to recommend if you have more questions, find Mung out there, and you guys can chat so we can stay kind of on schedule here. So thank you, Mung. Awesome. All right. Next up, I'm happy to introduce Harry from Exena, who's going to talk more about their work with CXL computational memory. That work?
Yes, that works.
Try this one.
Okay. That works. I will switch this.
Okay.
Hello, my name is Harry Kim, and I'm CPO at Exena. And it's good to know there is needs for hardware acceleration, and also good to know about Velox memory management. So Exena is a family startup bringing CXL to the data processing world. We are working on developing hardware and software solutions to accelerate Velox with CXL computational memory. So data is rapidly increasing, but we are reaching the limit of how small we can make a DRAM cell. So as a result, memory capacity, bandwidth, and performance are no longer doubling like they used to. So while data is exploding, we need better ways to process them. We often run into out of memory kills or suffer from performance drops due to disk spills. And in many cases, workloads vary so much, there are peaks, and that you need heavy tuning, like Meng said, or over provisioning just to keep up. So, and scaling out with more servers works, but bring with some more complexity and often diminishing returns. So how can we tackle this? What if a single node with dense memory and compute could replace an entire cluster of 10? This is where CXL comes in. CXL is a protocol built on PCI Express that lets you plug in your memory as the same way you plug in your GPU card. And CXL memory looks like just regular memory with additional latency due to protocol overhead. And it gives memory pooling or sharing with through switches. But to us, the most exciting part is that also it supports cache coherence, which makes it a foundation for heterogeneous computing, not just memory. So at Exina, we are building computational memory on top of CXL. That means memory can do computation, what's called near memory compute or near data processing. Our journey starts with building a high quality, high performance CXL DRAM expansion for the baseline, and then we extend it to use SSDs to create a much larger and more affordable memory tier. So we call what we call infinite memory. On top of that, we integrate thousands of RISC-V cores into the memory controller itself, and then build the software stack to drive them. To make this more useful, we also provide a data processing library which connects with a data processing engine like Velox. So our goal is simple: more memory, less data movement, get better TCO. Now, so CXL memory offers more capacity and extra bandwidth, but there's a little bit slower than main memory when it comes to latency. So when you put a lot of data into a CXL memory and access it through a CPU load store, it can hurt performance and waste power. That's why our approach is to offload some operators like scan, filter, or basic math to the memory itself. So the CPU doesn't have to touch that data at all. This reduces memory traffic and frees up CPU cycle, resolves cache lines, so CPU can focus on what it needs to do. We are building a custom SoC that combines CXL with a many-core architecture. It has over thousands of RISC-V cores supported by a high-performance cache hierarchy and memory systems. This is designed for large-scale workloads and parallel processing like vector database, Spark, Presto, or even graph analytics and DNA analysis. Yeah. The product comes as a adding card type like a GPU. We are going to use just RDIMM slot. It might have different form factor at production. You can plug it into standard GPU slots, and it gives you up to 2 terabytes of memory. We're launching this card by end of this year. We can use this card to build a memory pool with acceleration capabilities. Even more interesting, the cards includes a PCI root port, so you can directly attach SSDs to it. This setup gives you tens of terabytes of memory per card, cached by terabytes of DRAM. And this allows a single chassis to scale up to petabytes of memory. So let me give you some more detail. Exina controller includes an additional PCI Express root port, so we can connect SSD directly. So if necessary, multiple SSDs can be attached through a switch, and RAID setup can be used to enhance SSD reliability. Inside the SLC, we learned a paging algorithm that automatically caches SSD pages into DRAM and handles all the mappings and address translations. So you don't need to reformat data and invoke IO threads for disk spills. You just write to memory, and Exina handles the rest. Terabytes of DRAM tracks your active working set, and behind that, SSD gives you tens of terabytes of extra memory. Let's talk about acceleration. When you use accelerators, they normally require explicit data copies. You need move data in with, let's say, CUDA main copy, and out again when you are done. CXL is different. It's a part of CPU system memory space. When CPU stores data, it flows through the cache hierarchies and lands in CXL memory, so no memory copy needed. So this is huge. It means our CXL device can process data in place without wasting time or bandwidth on large data copies. But there are challenges. Applications run on the user virtual address, and CXL memory sits in the physical address space of the host. So for shared access, device must also support virtual addressing. And we must isolate each process's memory for security and correctness. That's why our solution supports cache coherence and virtual addressing, so we can offload complex or pointer-rich data structures without transforming them. This enables fine-grained offloading and lets the CPU and CXL device work together. Each can do what they are best at. And all of this works with our SSD-backed memory transparently. And of course, to use all of these hardwares, we need a strong software stack, like CUDA for GPU. Our SDK includes a compiler, libraries, simulators, and more. And we offer 3 layers of software abstraction, which I'll walk through now. So we started with a low-level device API to control threads directly. But as you might expect, it's complicated and requires deep hardware understandings. So not very productive for everyday development, and it's doable though. We don't recommend users to do at this level. It's too complex. So we created PXL, which is Parallel Acceleration Library. It's a runtime and API layer inspired by MapReduce. Now you can write programs with more familiar constructs like job or map objects. We are also working on shuffle side for reduction and planning to extend for graph workloads and communication primitives. PXL is available for internal and external development who want to write their custom kernels. So before we move on to the next third layer, let's take a quick look at how CXL hardware and software are structured. CXL memory could be accessed by CPU using standard load store instructions, just like any other memories. It's just a memory. So, but with Exina computation, things get more interesting. You can write programs using PXL to process data in place where it lives. This means the host CPU doesn't need to fetch the data and process it directly. That saves CPU cycles and avoid unnecessary case pollution, and that improves a lot for the efficiency to data processing. That said, parallel programming is still not easy. How many people feels happy with writing CUDA code directly? It's quite hard. Most developers prefer just using higher level frameworks like PyTorch. So that's why we are building another third layer like XFlare designed to process OLED queries based on open formats such as substrates or and Apache Arrow. So XFlare works as a backend for Velox, enabling query offloading and acceleration to the device. It's a plugin like a web project for GPU. We can use Presto or Spark through Gluten as a front end. We also provide a data-specific API called XVector, which is integrated with a Vice library for vector search queries. So here's a basic concept how XFlare works. XFlare integrates Velox through driver editor interface. It's similar with NVIDIA cuDF, and we want to keep minimal modifications in Velox. So it takes the Velox plan and transforms it to a local kernel that fits our hardware model, and we optimize it and chooses the best execution plan for each operators. So if there is high parallelism, then the operator will be executed on the device side. If strong single thread performance is needed, then the operator will be executed on the CPU. In some cases, it just falls back to native Velox. In this context, we want to work closely with Velox community to explore efficient use of CXL memory and to contribute to the Velox. So, call to action. CXL brings opportunities as well as challenges. Integrating Spark, Gluten, and Velox will not be easy. Memory management from different kind of software stacks are also challenging, and it's very important topic. We want to participate and invite the community to work together in reimagining the data processing infrastructure with CXL. And when you have time, please visit our website, exina.com/SDK, and you get some early hands-on experience with CXL computational memory. Yep. I'm super excited to join and being a part of this new journey of GXL and reshaping data processing infrastructures. And I think that's it for today. Thanks for your time.
Thank you, Harry. Thank you. All right. Our last session before lunch, I am happy to introduce Felipe from Voltron Data, who will be talking today about adapting ETL to real-world hardware chaos.
Yeah. Hi, so I'm Felipe Ramburu. I'm an architect at Voltron Data. And I'm going to talk to you all today about two different hardware systems and how you can change the way that you leverage certain parts of your software stack in order to make things more efficient. So for context, we're talking about distributed resource-constrained execution. So the data set is much larger than the memory that you have available. We're talking about an accelerator native engine. It's built on top of cuDF, RMM, NVComp, many other libraries that have come from NVIDIA and other people, and Velox, of course, and scalable centralized storage. So we're talking about things like Weka, S3, GCS. We have a centralized place to put it. First topic we're going to talk about is compression, when and where and how it makes sense. And then we're going to talk about task parallelism, especially as how it pertains to using faster and slower centralized file storage systems, or high latency file storage systems, I should be clear. For the compression section, we're going to be looking at compression that is done with NVComp. It's a great library for lossless compression on GPUs. We've been using it for a long time. The first time we used it, it was we emailed something to NVIDIA, which was our thrust implementation of this, and they emailed us back something much, much faster. When you might want to do this is when you're spilling data to host or to disk, or when you're communicating data between nodes. You also might have time when you're waiting on some kind of condition, something to happen so that you can move forward in your query, and compressing the data can basically reduce your memory pressure. So the first chart that I'm kind of showing here is we have, when you're thinking about compressing data for these ETL pipelines, you've got three phases that I'm talking about here. One is the compression phase, right? So you have to allocate buffers and space for where you're actually going to be putting this compressed representation. And when you're using something like NVComp, that space needs to be as big as the worst case scenario, which sometimes is bigger than the actual input data. Sometimes compression doesn't work. And you also have temporary space that you need to allocate. The next phase is compaction, right? If you had this big allocation, now you want to make it smaller so that it takes up less space in actual memory. And then the last is waiting time. How long is this data going to sit in a compressed state before I send it to another node, or decompress it in order to do some operation on it, or write it to disk? And what you can see here is that your uncompressed data, and here, these are all made up numbers, but the longer your waiting time, the more likely that compression is going to help you, right? Because you're basically saving all the bytes between your uncompressed data and your compressed data over that time period. the more expensive that compression becomes, or the more expensive that compaction becomes, say that your allocations become more expensive, and both compaction and compression become slower. And if your compression for some reason is slower, that's also going to make it less likely for it to be utilized. So I want to kind of talk about, like, when does this stuff happen, right? So when we have slow I/O, this could be because we have slow network. You often find this, if anyone's been running large workloads on the cloud, you might not, you might not think that it has always the fastest network interface cards possible. When you have slow file systems or high latency file systems. So S3 and GCS, while they can drive quite a bit of throughput, if you're using something like a compressed file format like Parquet, where you're decoding pages and decompressing pages as you're processing the data, high latency file systems can really, really slow you down, and being able to write and read to them quickly can definitely help. You can definitely improve that with compression. Another time where this might make sense is when you have pipeline breakers. Let's say you're doing something like a global order by. At some point, you actually have to make sure that you've ordered all the data and made all your necessary comparisons to make sure that that you actually have a globally ordered data set. And compression can help you so that you minimize the amount of space that you're consuming while you're waiting for this condition to be met. Places where it might not make sense is when you have, especially on GPUs, is when you have really small batches of data, things like smaller than a megabyte, where the overhead of making that GPU allocation and copying making that allocation and making kernel invocations is going to take longer than it would have been to just pass that data along. Other places where it's less likely to make sense is over things like NVLink, InfiniBand, and Rocky. So if you look here at this image, I'm showing where we've got a GPU that's connected to a PLX switch alongside 2 NVMe drives and 2 network interface cards. In this kind of situation, where you have relatively high bandwidth between these devices, where you're not having to go to host memory, go over PCIe, in order to be able to get information from the GPU to the network interface card or to the NVMe, somewhere else that it needs to go, then it makes less and less sense, because you need to be able to allocate, compress, and decompress faster than these higher throughputs. And when you're talking about things like NVLink, then you really can't compete. The amount of time that you spend compressing is 100% going to slow you down. The other point is data that is about to be operated on. Unless you can do operations on compressed data, which is a separate topic. So the next thing I want to talk about is task parallelism. In this context, by task, we mean a group of work that's executing on one thread with its own CUDA stream of execution. They might be performing file I/O, allocations, GPU compute, memory copies, might be sending data to another node. And while the number of tasks that exist at any point in time are varied, and their execution is independent of each other. So the first thing that I want to look at is, here we have an example of all these tasks that are being done here. There's 5 at a time and maybe like 20 across, so 100 tasks. These are all actually scanning from GCS, if I'm not mistaken. This is being done on GCP. And in this case, we're doing 5 scans at a time, and this is a query 5 from TPCH's 10 terabyte run, so a 10K run. And on GCP, this is taking us about 120 seconds of wall time. And what we can see here is that we actually have pretty, we're not able to feed the GPU fast enough, right? So as we're reading from S3 on only 5 threads, we're not really spending any time waiting for available memory. So we know that we don't have that much memory pressure. And if we go up to 15 consecutive scans, as we have here, we're actually able to save about 30 seconds off the query and only incurring about an extra second of waiting for memory per thread. In this case, we have 15 threads because we're able to drive more I/O from S3 and hide some of that latency. Here we have an example of using GPU direct storage. This is run on 16 A100 GPUs. And you'll find that when you have much, this is also done on a node that has, it's using Weka instead of GCP. We have much higher throughput, much lower latency, and we're able to leverage GPU direct storage to move data directly from, if you go back to this image here, we're able to move data directly from Weka to this network interface card and into the GPU over PLX without having to go through host and all that other nonsense. So what we find is that on these much faster nodes, you don't need more parallelism to drive execution. These yellow sections here in the query are actually where we're having to spill some of our GPU memory to host memory. And so on just 5 nodes, on 5 execution threads, we're able to drive all the usage that we want on these 16 A100s, right? This is per GPU. So we have basically 5 threads driving execution per GPU. So where does task parallelism help? It helps when you need to hide latency. So things like S3 and GCS. We'll obviously need to have upper limit and back pressure mechanisms when you're doing this in order to make sure that you're not spending all your time having to spill to disk immediately after you bring things onto the GPU. And you also need to worry here about resource contention. Tasks can have very high variance in terms of resource utilization. So if you've been working a lot with UDFs, you might find that users can do some pretty wild things in user-defined functions. And so you need to have ways of being able to manage that resource contention and be aware of how your tasks are going to be impacted by this parallelism. Joins and grouped exact count distincts are other examples. And this works best when your tasks are consuming diverse resources if possible. If they're all hammering on exactly the same thing, then it's not going to yield as many benefits. Places where this really doesn't make sense is, an example I gave before, like UDFs, building an index for vector search in a UDF, for example, would be very, very slow. Not very, very slow, but is not a thing that you can run on tons of different threads because each one of those tasks has a pretty high memory requirement. The other places is low latency storage. So when you're using GPU direct storage on NVMe and Weka, as I said, this kind of stuff really becomes much less of a problem, and you're more focused on being efficient with your GPU compute. GPU direct storage does a hell of a lot in order to help you avoid some of these, some of the slowness that you can see on S3 and GCS. So that's it. That's my talk. But I'd love to take some questions if anyone has some.
All right. I think we're going to lunch anyways right after this. So if people have questions, they can probably come find you, right?
Yeah.
Cool. Thanks, Felipe.
Thank you.
All right. So look at us. I think we've ended like early. So now it's lunch. So feel free to help yourself, and we will be back here at 1:30. Enjoy. Hello? Oh. All right, we're going to try to get started on time here. So it's 1:30 on the dot. So please come on in, take your seats, folks. All right. And I'm happy to introduce Nathan from Chalk, who's going to be talking about real-time ML with, I can't see your, sorry. You can do quit. Accelerating Velox and Python. All right, thank you.
I'll use this. Hi, I'm Nathan. I'm a software engineer at Chalk. We're a small startup that's working on a compute platform that makes it easier for smaller teams to develop large-scale feature pipelines. Basically, the problem we're trying to solve is making it easier for teams without lots of infrastructure experience and query planner experts, like everyone here in the audience, to ship models fast and incorporate new data sources. Oftentimes, teams end up having to do complicated ETL pipelines just to get data that they want to add to their database, even though they know another database that they use all the time and is perfectly capable of serving stuff on demand is used for other products outside of machine learning. And this is important because they want to be able to react to real-time signals. If you're looking for patterns of fraudulent behavior, knowing what happened yesterday is not going to be any good at spotting 10,000 fraudulent transactions created over 10 seconds. So what Chalk does is we compute your data on the fly so that your features come from whatever their original data source is, whether that's SQL or some API that a vendor provides, or derived from other feature values that you also want to keep up to date. So we do this with a bunch of things that we call resolvers, which are blocks of computation, functions that are made of SQL, APIs, Python, or whatever else you might want to build, that we then stitch together automatically to serve both online and offline queries. Of course, the distinction here is important because online queries need to happen in response to user actions. And so this is someone makes a payment or they click on a link and you want to show them recommendations. And that means that you need to respond quickly. So low latency, like less than 100 milliseconds, so it's roughly instantaneous, is an ideal target. But you want to do this rapidly, hundreds of queries or thousands of queries per second, which is very different from the training offline case, where you're trying to build historical data at high row cardinality with larger than memory workloads. But what a lot of teams struggle with is, because the performance characteristics are very different for these two kinds of systems, they end up building the system twice. This makes it hard to evolve the system, because whenever you want to add a new feature, you have to go update it in two different places that behave very differently. So what Chalk is doing is we're using Velox as a common compute engine for both offline and online queries. So in this talk, I'm going to just focus on online, because we've had lots of talks about scaling offline to billions of rows. So this makes productionization a lot easier because you write it once after your experimentation and it's ready to go. We manage the configuration automatically with lots of helpful tooling. So here's what it looks like. We want to define features declaratively so that we're able to look them up later beyond just a bunch of SQL tables or a bunch of parquet files. And so we do all of our configuration as Python code that we ship as one large unit and do analysis on to build a feature graph. So it's just a Python class with an annotations of @features at top as a decorator, and then we read all of the types in order to produce an arrow schema for this, whatever this class is. This allows us to do basic features, float strings, but also more complex ones like lists and maps and structs. And it also lets us define relationships between different features. And this is really useful for making it possible to evolve your data over time. So in this case, for example, we see that every transaction belongs to a user, and every user has many transactions that it can access through a data frame that contains them, or in particular, contains whichever columns of them it wants to use. So resolvers are how we actually compute those values. And the most common kind, because SQL is king, are SQL resolvers. We're able to just define a SQL file that resolves some subset of the columns of any particular feature class. In this case, we have one that selects 3 different columns from some Postgres table to resolve those fields in the transactions table. But we're not we're not restricted to one database at a time. We can also have a BigQuery table that resolves some other set of columns. And in particular, if we only need some of them from one of these two places, we know in advance where we need to get them from. But if we need both, we can just pull from both and join them on the fly. This is sort of like the feature insertion process that the Metalike talked about yesterday, in that we're just stuck in the slow case where we're still constantly pulling from 2 different data sources, but we find that we can get this to be more than fast enough to serve our users. And it gives them much more flexibility because they're able to instantly add or remove any feature column that they want from any data source. And since these are just SQL, we're still able to do SQL pushdown. So we execute these primarily as UDFs inside our existing Velox plan. And so this allows us to easily support any number of databases from Postgres to SQLite to BigQuery, etc. And the other big kind we have are Python resolvers. And so Python resolvers are just Python functions with annotations on the inputs and outputs that tell us which features they represent. So for instance, we might have a get user from API that takes in a user's ID and returns their name and email, or we might have something that takes in the recent transactions amount category with a filter on the date being recent, and it will return the user's recent transaction volume using some kind of formula that the user defines. But these are really arbitrary Python. So of course we can do like data frame pandas style operations or polar style operations where you take in some data frame and do that. But you can also just like throw in an HTTP request or have a stateful client or whatever else that it is you want, because we're really running Python in order to load whatever this data is. The other thing we have is we allow for easy point-in-time historical queries and easy cached values for the current data. And so you can simply attach a max staleness to any feature value to indicate, oh, here's how stale I'm willing to allow this feature to be. Then when you want to load it, we will first look in the online store to see, oh, does it exist in this Redis cache? And if so, we can skip running whatever resolver and whatever inputs that resolver might need and just deliver the value immediately. And so you can take something that, say, is fresh 99% of the time and then vastly reduce your cardinality and therefore reduce your latency in loading it. So our query planner basically looks like a sort of traditional build system in that we have a list of output features that we're looking for, and then we're going to sort of go backwards through the resolvers that are available, finding the ones that resolve those features. And while we do this, we're also looking for relationships across them so that, for instance, if you want, the user wants the transactions table and the transactions has derived fields that come from some other table, we will continue going down looking for more resolvers until it eventually resolves everything. So here's an example in our web UI of what like one of these query plans actually looks like. So this is like 10 plus Python resolvers, 5 different Postgres lookups, 2 different Redis online store lookups for different namespaces, and this whole thing ran in 68 milliseconds in one of our dev clusters. So it's pretty straightforward to sort of add and remove any number of features that you might want to load, which makes the developer experience for this really nice because it's very declarative, it's very easy to change things. And so, of course, we're actually executing that on Velox. So each of those little boxes expands to 1 or more Velox operations. Sometimes it's just turning a Python call into a UDF. Sometimes we're doing a join. Sometimes we have to apply extra filters in order to make point-in-time queries correct. But we're able to sort of expand this into this much larger plan that we're then actually running. And again, this particular one ran in 68 milliseconds. And so here's like a zoom view, so we can see that some of the like common operations that happen. We've got like a UDF that is actually performing an online store lookup from Redis. We've got some joins, we've got some projects, all very like standard operations. And so we have a bunch of optimizations that we've applied on top of Velox in order to make it better at doing these sorts of online queries. And so one of the big things is we have replay. Because we have resolvers, which are potentially very slow, we want to avoid running them multiple times. And so while we run them, we record any data that we might need effectively as a materialized CTE. We call this replay, where record batches that are going to be needed twice, such as this SQL result here for 2 different parts of the plan that we want to run concurrently. It will be duplicated into a replay network so that we don't have to compute any of those values twice. And it also counts how many times they're needed so that it doesn't hold them onto them any longer than is necessary. And this is important that it's in memory for the online queries, because otherwise we would have to spill, which would mean copying, which would mean extra latency. And so all of the record batches are typically held in memory until they're going to be needed. Another kind of optimization we find is that we have a lot of hash joins in our plan because we're doing replays to avoid duplicating resolvers, but that means we eventually have to combine the data back together. And what we found is that the Velox's hash join on the build side converts from a column format to a row format because it needs to store each of the rows into a hash table so that spilling is possible. However, we don't want our online queries to spill because that would mean touching disk, which would be very slow. So we have a custom online hash join, which is essentially a fork of the original hash join, which is optimistically 0 copy. It keeps the original build side record batches in memory so that it can select individual rows from them instead of needing to copy, and we found that in end-to-end in one of our like typical queries, this was 1.4 times faster. The other big thing that we've done is we've noticed that when we have very low latency targets, like say 50 milliseconds or less, a significant portion of time is spent on Velox analyzing the expressions in the plan. So some plans will have like 10,000 expressions, which isn't that many. But if you spend a microsecond per expression, that ends up adding to multiple milliseconds of overhead. And this will run every single time you want to run the query before you even have the data to run it. So on one particular giant query, we saw that 50% of the CPU time that it was spending was spent just on expression initialization before it was even looked at the data for those expressions. We were able to reduce this by 17% just by caching expression equality and rewrite rules. We were finding that it would repeatedly compare the same expressions over and over to each other, even though they're not changing whether or not they're equal, and it would apply rewrites that don't go anywhere. So by caching this, it was 17%, and we got this even lower by caching expression set initialization completely. Every project and filter has a expression set that has been expanded into a pool of already initialized expression sets. Whenever a new query comes in, it will reuse one of those initialized expression sets or create a new one only if they weren't already available. Lastly, we run a lot of Python because we want to make it really flexible and easy to define new features and new derivations of features that are going to go beyond whatever our ideas of the operations that you want to perform on your data. Our customers always have their own ideas. So every Python function has a strict arrow schema for input and output because we know what the feature classes are, and so we just have to convert from Velox to arrow to Python to arrow to Velox and back in order to be able to run them. This is a little bit inefficient, but being able to use arrow as a common format makes it a lot easier to interop with the existing Python tooling. And to actually run them, we have a pool of subprocesses that receive requests for chunks of the input record batches that we receive and run them in parallel. But in practice, this is great for flexibility. It's really easy to define new ones. Engineers and data scientists like reading them, but they're really slow. And there's lots of reasons that Python is not as fast as Velox, which should not be surprising. It struggles to run multi-threaded code. It has heavy types, heavy type representations because of dynamic types. Every int and string and float is going to be a heap allocated object. And obviously, it can't do simd if you're writing a bunch of operations that take one value and add it to another one. But who are we to say that our users shouldn't write a plus b as a Python resolver? So we have Velox. It solves these problems. What we've done is we've noticed that a vast majority of the Python resolvers that people write are really just doing basic data cleanup and transformation. So they'll check, for instance, in this case, that the discount is not none, and if it is, then they'll modify one of the other values by reassigning some basic functions. They'll have an early return or some various checks for edge cases. And ultimately, they're usually doing arithmetic or string manipulation or array manipulation, etc. And Python is really nice to write this. It would be annoying to write this, for instance, in SQL. You totally could, but it's not what people would usually reach for this kind of transformation. So our breakthrough is that we have a symbolic Python interpreter. At query plan time, we look at all of your Python UDFs, and if one of those UDFs has the form of one of these pure compute operations, we will convert it into a Velox expression directly, so that at runtime, there's no Python involved. And the way we do this is what I'm going to go over now. So basically, we have an environment that stores a mapping of each Python variable name to the corresponding underlying Velox expression, along with metadata, which describes what the Python type would be if we were running Python. So initially, these are going to be column expressions corresponding to whatever column we happen to be running. So for instance, the discount we know comes from some column, say, named D, and subtotal comes from S, etc. And these will refer to the original value that was plugged into the Python value. So when we have a Python expression, we just have to evaluate it like we would if it were Python, but we replace the result with a new Velox expression that does the same thing. So for instance, a Python subtraction, we look up the corresponding values. They're both float types, and so this means we'll just be able to use plain old Velox subtraction on the results, and it would produce a Python float. And so we're able to then take this value and do more things with it. For example, if we have a reassignment, we just evaluate the thing on the right into whatever the corresponding expression would be, which in this case looks exactly the same, and then we replace it in the environment. So all the other variables hold their old symbolic values, and the one that was reassigned, in this case, whatever x equals y, the x value is replaced with a new symbolic value. And for if statements, it starts being a little bit more complicated because we now need to deal with conditions. We start by evaluating the condition itself as an expression like normal, and then we're going to evaluate the two sides. So the true side will produce some environment. This is what would be set in each variable if the condition had been true, so we had run the true side. Otherwise, we're going to back up, and we're going to do the same thing for the false side. So we'll see if the condition was false, this is the Python code we would have run, and this is the resulting environment that we would be in. And now we just need to merge them together into a composite environment, which is what's true in either case. And so we just take each variable and say, oh, if the condition was true, then we would be in the left, otherwise we would be in the right, so we wrap them in an if then else, and this maintains the original semantics. And of course, they're already equal because our symbolic values don't have side effects, we're just able to leave it alone. And this is usually what happens. Lastly, we need to do with actually returning values that we're able to extract them out. So in addition to the environment storing variables, it also stores a list of early returns. So if we say if GHI return MNO of X, otherwise, if PQR return VWX, etc., all we do is maintain a list of conditions with return values. And so again, the conditions are going to be the symbolic value of when this is the case, we return this value. And we just go through them semantically in order and take the first one that returns true. And if none of them do, we have a fall-through environment that still stores the values of the variables that we'd get if nothing had returned. But the result is that we're able to take this code from before and we're able to convert it into an exactly equivalent Velox expression. We've done a lot of work to make sure that we always guarantee that the semantics of the resulting Velox is the same as the initial input Python, but there's no actual Python in the result. And so we don't have to tell people, oh, if you're doing basic arithmetic, don't write it in Python. They're welcome to do it whenever they want, however they want. And so what this gives us is that Python is a DSL, a domain-specific language, for writing Velox expressions. We don't have to teach people about a new kind of thing in order to run the Python that they want to run. They're able to just write Python, and we execute it in a much better format that works much better with the rest of the Velox execution that we're doing. So automatically, there's no GIL, so we're able to run it multi-threaded. All of the heap representations are gone. We're using the same flat vector arrays that every other Velox expression uses, and we also get SIMD for free without having to actually tell users that this is even a thing. If they're running multiple rows of input, it automatically will add numbers together in parallel, for example. And then to make this work in general, we have a lot of support for fallbacks. So we have some partial fallbacks where a function, say like date format, we might accept certain types of date formats, but we might have struggled to emulate the error precisely. But the vast majority of code that's flowing through the system shouldn't be generating errors, and so we will assume that usually we'll get a successful conversion. And so in that case, we will dynamically try to run the Python as a converted form. And if we detect we fall into a case that can't be parsed using the formats we expect, then we will fall back and actually run a Python UDF. And so this means there's only Python involved in this rare error case that usually you won't encounter. Some functions we just don't support at all. And so in that case, we still have a Python runtime, so we're able to run things in parallel in subprocesses to do whatever work is necessary. And lastly, we have a gas limit, which identifies certain pathological cases which would either take too much time to compute or just otherwise wouldn't be good candidates to run in Velox due to, e.g., accidentally making code quadratic. But we also support a bunch of other things that I haven't mentioned, such as for loops and mutable arrays, so that, for instance, if you loop over an element, loop over one list and append into another, we're able to turn that into a reduce or a transform or a filter. Yeah, but we're still continuing to expand our library functions for it. So basically, the result of this is we're able to make it really easy for users to define new features and new transformations on features because they just write Python, which they already know about. That's not going to be new to them. But this means that it's automatically fast enough for real-time inference. If they want to do something crazy and import some library we've never heard of, they totally can. But as long as they're doing simple data transformations that are predictable and very Pythonic, they'll be able to run them as Velox expressions without any effort on their part. And so it makes it much more approachable to build these kinds of very complex plans and still let them run in production at scale. So this makes it much easier for teams to iterate. Yeah, I think that's time, so.
Yeah, I think first of all, that's super cool. We've been discussing about this for PyVelox for a while, like if there was a way to kind of express the UDFs themselves or the expressions in Python. So I think my first question is this open source or something you'd be willing to open source?
Not yet. Currently, it is very tightly integrated with certain other parts of our backend. We've considered it, but it's just not possible yet. We'll probably be looking into it, but yeah.
Yeah, if you're willing to contribute that to PyVelox, we would be happy to take the contributions. Last question is, you mentioned inference. Is this like the feature store thing? Is it something used for training as well, or is it mostly for inference?
I didn't really have time to talk about it. We also have an offline thing, which is essentially equivalent, so you can run the same resolvers and get larger tables however you want. we have the same kinds of things you'd expect. So you can have like a large table, ETL it to some database, or we also have an offline store that essentially stores every feature value we've ever processed, so you can query that however you need.
Nice. Yeah. Very cool. Thanks.
Back here.
Hey, thanks for it. So question on the SQL resolver, right? How should I understand it? Let's say, like the examples that you spoke about where a BigQuery and a Postgres is involved. So in this case, how much of the role is Velox as? Is like Velox acts as a wrapper, pushing down everything into those sources, and only if I have a need to join, that's when Velox comes into effect. And secondly, if it acts as a wrapper, like, is there a trade-off on what to push down, or is generically if it's a SQL, push down everything to sources? Like, how does that trade-offs happen?
Yeah, so basically we're essentially wrapping a real client for whatever library you happen to be hitting. So like if you're a BigQuery client for BigQuery, or Postgres client for Postgres, et cetera. And then we just stream the record batches out. We have done a lot of work to sort of push down as much as we can so far. Like for instance, if you have a Python resolver, you can include an annotation that says, for instance, I only want pending transactions. And then that kind of filter will be pushed down automatically. We don't currently get everything, but we're trying to sort of expand so we get more information that, for instance, if there's an upstream filter or an upstream join, we will automatically apply that. We currently have heuristics that cover most of those cases, but not all of them. We want to sort of commit more to like using the information that Velox has.
Firstly, really cool presentation, and I think very interesting topic. Also want to strongly reinforce Pedro's point about open sourcing. I think we'd be very interested. One more question. So you talked about arrays and loops, and you're converting them into for loops into you're able to like also transform for loops and stuff into select UDFs. Is that in general, or is it a specific case? And the next point also is like, so this only works for expressions. Are you able to have aggregations, or have you thought about like moving, getting aggregations and other operators also on your DSL?
Yeah, so to the first point, essentially all of our transformations are general, but there are a lot of specific cases that will trip them up. So depending on how complicated or how convoluted your code is, it might not work. Generally, our goal is that like straightforward code will work. So we start with for loops, for example, by turning them into reduce expressions over whatever the like array reduce expressions over whatever it is, mapping whatever state is necessary to make that happen. Certain kinds of things that you can end up doing don't work inside them, but we're continuing to expand that. To your second point, we have a separate system for non-Python resolver definitions that are also not SQL that we call chalk expressions or underscore expressions. Those support aggregations, and so we're working on combining them together. So essentially that, for instance, if you take an input that you declare is a data frame and you call .sum, then we will turn that into a aggregate. So that already happens in the other case. It doesn't yet happen on the Python side, but we're working on that.
Okay, cool talk. Thanks, Nathan. Okay, so next up, I want to welcome Yunfei from Uber, who's going to be talking about Velox reading column encrypted parquet files for column level access control.
Hello, can you hear me? Okay. Good afternoon, everyone. I'd like to share some of our recent work about Velox reading column encrypted parquet files for column access control, column level access control. So this is agenda. We will first talk about what's CRC and Apache parquet format. Then I will talk about like parquet encryption decryption mechanism, and also parquet decryption flow, and how to enable parquet decryption in Velox. Because Apache parquet file format is the main file format used in Uber, and we use Apache parquet's column, encrypted column for access control, column access control. So why do we need a parquet column access control? Because it enhances data security. It protects sensitive data at the column level. like some column, they may contain like sensitive data, like maybe user PI, like a username, email, or address, and also some business confidential data. This data should be encrypted at rest, and also its access should be controlled. So only permitted users can access those columns. Parquet CRC can also help improve performance, because when we reading a Parquet file, we only need to decrypt the columns that are encrypted. With other columns unencrypted, so to reduce overhead of encryption and decryption. So with Parquet CRC, it can promote compliance and trust. It helps align with industry standards and legal requirements like GDPR and HIPAA. And it also increases confidence among stakeholders and customers regarding data management practices. So yeah, let's take a look at what's like a Parquet file format. Parquet file format is a columnar storage file format. This feature makes it possible and easy for us to do column encryption and access control. So like this is an example of a Parquet file format. At the beginning of the file and at the end of the file, there are 4 bytes of the magic number. You can use this magic number to check whether it's encrypted or unencrypted, and also combine with another field later I will show to check whether what encryption mode it is. So on the left side of this graph, when you write a bunch of rows into Parquet file, it divides rows into groups. And each group is called a row group here. Inside each row group, the value of same column will be stored together. I think that's why it's called columnar storage. Like here, like inside row group 0, it has column A and column B, and maybe some other columns. And for each column, it further divided into pages, like page 0, page 1. And each page contains a page header, which has the metadata of the page, and also a page body, that's the data itself. On the right side, from the bottom, besides the magic number, it has a footer length. It denotes like what size of the footer, so that initially when we write a Parquet file, we can first write all the footers into memory and deserialize it into a Swift data structure. So besides some global metadata, the footer mainly contains the metadata of this Parquet file. Besides some global metadata, it also has like row groups. This row group correspond to the row groups on the left side. So for each row group, it contains metadata for each column. So Parquet encryption has 2 modes, plain text footer mode and encrypted footer mode. For the plain text footer mode, it encrypts selective columns and some of the metadata. Like this metadata may contain some confidential information. For example, like a minimum value, maximum value, and so on. For the encrypted footer mode, in addition to what the first mode does, it also encrypts the footer as a whole. So this is a plain text footer mode. You can see in this example, column A should be encrypted, right? On the left side, its pages, like page 0, page header, and page data are encrypted. On the right side, for the column A's metadata in row group 0, some metadata was encrypted using this column key. And also the encryption metadata is stored in this column crypto metadata. It may include like the encrypted key and also some other metadata about the encryption. This is the other mode. Like you can see, it has the whole footer is encrypted with a footer key. And how do we do CRC via Parquet encryption? Like when we write data to a Parquet file, right? Some columns, they need to be encrypted, and different columns can be encrypted using different keys. And here's the keys we call it working keys. And after we use working keys to encrypt this data, the working keys themselves are also encrypted by calling key management server. In key management server, there are master keys. Those master keys are used to encrypt the working keys. The encrypted working keys will be attached into the packet filter along with the other column metadata. When we're reading a packet file, encrypted packet file, we will send a request to the KMS to decrypt the working key. We also send the users, like a query owner's information, so that the KMS can decide whether this user has permission to decrypt the key. So the CRC is controlled by the KMS. So this is a simple flow of the decryption. Like when we read a packet file, we first read its footer, the metadata. Then in the metadata, we get the crypto metadata, the encrypted working key, and maybe master key name and versions, those kind of metadata. Then we call KMS to decrypt the encryption key. Then we get the original encryption key, use this encryption key to decrypt the data. So the main change is first in the packet reader. In the packet reader, we need to pass the crypto metadata together, the encrypted key, and then use it to call KMS to decrypt this key. And the other part is in the page reader. When we get the original encryption key, we can decrypt the data. We first decrypt page header, then decrypt the page data. This change, we just send a pull request. It's still in review. Like when in the future, once it's landed, if you also use the packet encryption and want to use this decryption flow, you need to first provide your own KMS client to talk to your KMS. So we also provide a reference implementation of the KMS client. You can extend it and implement the method. So maybe you will need to do some authentication when calling KMS. So we also provide some caching in this client, and so if some columns they share the same encryption key, so it can save you some requests to KMS. So after you implement the KMS client, you need to enable CRC in config. So by default, this CRC logic doesn't affect the existing code, your flow. Okay, in the future, we may also want to support encryption in packet writer, and also to support encryption for another encryption mode, encryption footer mode. Yeah, that's all. Thank you.
Hi. How do you take care of interoperability? These files, can they be used by any other products, even at least for the unencrypted columns?
Mm-hmm. Yeah, so in a packet file, you only selective column are encrypted. So if your query doesn't access the encrypted file columns, it doesn't affect it. For query access encrypted, like encrypted columns, when you read the packet footer, you can check whether it has like a crypto metadata. If it has a crypto metadata, it means it's encrypted, and you need to decrypt it. Yeah.
Thank you.
Yeah.
Did you implement this in Uber independently, or are you using the Arrow Parquet implementation?
So for the encryption, the algorithm, that part we use Arrow. Okay. Yeah.
Is there anything that you implemented specific to Uber internally?
We removed the Uber specific logic,
cool.
So this is should be general enough. Yeah.
Thanks.
All right. Thank you. Okay, so next up we have Rajan from Data Pelago talking about next-gen data processing architecture for heterogeneous computing infrastructure.
Hello, good afternoon, everybody. First of all, thank you so much to Meta and Velox team for hosting us here for the wonderful conference here. So thank you so much. Let's give them a hand to the Meta team and the Velox team. My name is Rajan Goyal. I'm CEO and co-founder at an early stage startup. We are headquartered in Mountain View called Pelago. So as Ali said, I have two topics that I wanted to talk about today. How do I do this thing? The red one? I can use this
Somebody
thing.
have the other clicker? Let me just make sure this doesn't work. One of the presenters took the other one?
Okay, I can use this one. So as I said, thank you. I have two topics that I wanted to share. One is what the next generation accelerated data processing stack should look like, or what have we built. And second is I also wanted to motivate a need for a new benchmark. Not that we need yet another new one, but at least motivate that why do we need what we call DP mark, and I'll share some details about it. So let me first talk about a little bit where we come from as a background. Not so much about the company yet, but previous life, some of us spent a lot of time in the domain-specific computing, doing hardware, software code design, building domain-specific processors. If you have heard the term DPU, one of the third pillar for data centers to enable disaggregated infrastructure, we were involved in that. So there is prior knowledge of hardware, software code design or accelerated computing. So this is kind of a culmination of multiple journeys of data as well as accelerated computing coming together. That's when we formed the company in 2021. And there were three, you can say, irreversible trends. One is we are entering an era of heterogeneous computing, which I'll show in the next slide what we mean. Growth of data and also untenable cost of data processing. This is what led us to the forming of Pelago. But right now where we have a production-ready platform built on many of the principles which were shared in today's or last 2 days of presentation, but I'll share some snapshot of those two details here. So the first is we come from the assumption that if you look at the more step back and a broader look, that the data centers we are into a heterogeneous computing era or domain-specific computing, where the reality is that all the data centers will have heterogeneous computing element, not just GPU or CPU, but many more than that. So why is that? If you look at the history of the various computing elements, even the CPUs are now SoCs, system on chips. You just don't get cores, you get a bunch of accelerators also built in, whether you notice them or not. You have zip, regex, data movement, and depending upon the variety of the processor, they're all system on chip with a lot of cores as well as some hardware accelerators, inference being one of them, the most recent ones people are adding. Then obviously GPUs, we know the journey, how we landed where we are right now. And FPGAs also, which started with the glue logic. And many of the people in the audience may recognize that. But now FPGAs also have domain-specific processors or logic plus the programmable logic that they are being used for application. So and many more TPUs and XPUs and many more processing elements are coming in the data center. So that is the reality we are born in when the data center is all heterogeneous. And if you want to design a data platform for this new era, what should that look like? So that's a view we take from that. So now let me begin. So what should the data stack looks like in this new reality? So assumption is that if you double click on whether it's an AWS or Azure or Google Cloud or any other large cloud, you would see a variety of servers, not just the homogeneous server which used to happen. And the second thing is that, as we know, scale-out card has been played out. So if something has to happen, CPU plus something has to handle the workloads that we are talking about. And that something else is a variety of servers, variety of processing elements. And then on the top, we have applications, whether it's a GenAI in context or data processing or analytics or BI or ETL workloads we have been talking about. They're all having a common programming language, whether Python, SQL, or Scala, or many more. But we don't want to have any change at that level. Otherwise, it's going to be disrupting the user's ecosystem. So what should that empty space in between look like in this new reality of heterogeneous computing era that we live in? So that's the view we take. So what we thought of that, how to fill that empty space, the data processing stack, the very first layer we built or we want to build is a virtualization layer. So that is what we call data VM. The idea is that if you want to build it for CPUs only or GPU, and then there's an FPGA, then maybe there's a TPU, or even the processors have, Rivos was presenting today, they may have some hardware hooks, or Ampere has their own ARM processor with some other hooks. And this is inevitable that all the CPU vendors will want to differentiate from each other by adding those hardware accelerators. And data processing being the largest computing spend today in the world, everybody want to focus on that. So that's a new world. So that means that when you are born into this era and you want to make it a more future-proof, you want some kind of abstraction to do that. So what that abstraction looks like is what we call data VM. It's a domain-specific virtual machine. If you think about it, it's in a processor, but we implement it in a software. And that virtual machine is written in a viewpoint of a data flow graph itself. So let me just explain what that VM looks like. Think of like a processor, but implementing it in a software. But just like we used to have C++ as a data-oriented language or something, it's a similar way, it's a data-oriented processor. So if you look at the left-hand side, you have a compute unit, like an ALU in a processor. It has input channels, which could be the input arcs of a data flow graph. And you have output, which is the outgoing edges of a data flow graph. And then you have some registers files on the right-hand side. And you have your program instruction cache or instruction code with a program counter. That's a typical ALU. And the way to think about is that this is a stenciled out many times if you think as a node of a data flow graph. We are all familiar with the data flow graphs, how the programs in our SQL world get represented. So each of this ALU represent that node of a data flow graph. If that is the way to look at it, you have input edges and output edges, and some context stored in that node is what the ALU. So that is what the data VM is. And now this can be copied n number of times and to do that. And the instructions that it will support, obviously, there are map instructions, reduce instructions, you can generate for testing or whatever, there's a scalar instruction, and obviously just like any ALU, it has control instructions. You can have your branches, your if and else, and all those instructions are part of that. So let me give an example of how that looks like in reality. This is actually working as a production virtual machine. So left-hand side is just as a contrast, I'm showing how a typical x86 CPU instructions looks like with its own control instructions, load, store, and add, and multiply. And right-hand side is what the sample program for that data VM looks like. Remember I said this data VM is implemented in software as a layer, but we can build a hardware also later on, but that's not the intention here. But it is a full-fledged processor with its own domain-specific ISA. So if you look at the logic here on the right-hand side, it says end of stream for all, and it's a bunch of R8 is output where it marks Boolean, whether it is end or 1 if it's end of stream. And then you have 3 inputs edges coming to this node, this program, I0, I1, I2. And those actually represent the upper green input panel. Those are the input edges to my node. So imagine in this case, there are 3 edges coming to my node, right? I0, I1, I2. I could have EUS.any. If any of the edges end, or if all of them are end, generally when we are processing at a fixed size block with the same number of rows coming in, let's say you are feeding 3 different columns, then they will have the same number of rows. But you can have it more flexible that if a particular block has less number of rows, maybe they're compressed or whatever. So it does support that. And end of the day, whenever it is all or end of stream, it sets a register R8 with 1 or 0. So then there's a compare logic to compare whether it is end of stream or not. Think of like a program. Nobody is supposed to write this program, but this is what the data VM exposes. and upper layers, which I will show you in a second, generate this code automatically. Then there's a branch instruction. If you have reached the end of stream, you go to jump to the program counter +7, which is at the done, and now done with the code. So that is your simple loop of how the loop is implemented. But if you focus on those 4 instructions that I'm showing, that this processor, even though implemented in software, has a parse instruction, a select instruction, project, and hash.build. And I'm sure all of you recognize that. So in this case, parse instruction can parse a JSON file, JSON record, with a schema, which I'm listing here as a ID field, some address repeated n number of times, which is ordered, and the address has a schema of a street and the zip code, and there's a data type of street and thing, and there's some schema of how you're expecting the JSON records to have that, right? So you define the schema, and the source it is showing is coming on I0. Remember, it is having 3 inputs coming, I0, I1, I2, in the first instruction. So this JSON record is coming on my input node, input edge I0. Maybe this node in the data flow graph has 3 different inputs coming from different sources. So one of them is a JSON record. So that is coming on I0. Some context, maybe just to retry or whatever is stored in R register 20. And once it is parsed, put the output of the ID into O0 for the next node. That's what this instruction says. So, and then and the target is, which I will introduce, because we support heterogeneous computing elements, you can execute this on an FPGA or on a GPU or also on the software CPU, but that is not designed, that is not controlled by the user. Automatically system decide, which I will explain in a second, who decide and why it is decided, where is the target for this instruction. But that's just the instruction definition with its opcode, with some kind of a operands. In this case, it happened to be the schema, and what is my input and output, and where to execute it. That's kind of the standard format of this instruction, right? Now, and then I have a select. You can say it looks at the input, puts in the output O10, and predicate on input I1, which is a next input edge coming to this node, and it runs that predicate some expression, and if it is greater than 10, adding I0 plus I1 greater than 20, it's kind of S expression over here, prefix way, and then if it is greater than 10, it puts that bitmap into the output port or output edge O10 as an example, and then it does the project. And then similarly, you can want to build hash join or whatever. There's a hash build. You can have hash probe. And in this case, you can decide in hash build case, what is my function murmur 32. Height 20 means it's 1 million entries to begin with. And if you fill it, if it's overflow, how do you handle it? There was a question in the beginning, in the morning, that if my data is larger than my hash table you begin with, how do you handle it? How do you spill it over to host memory? Or do we resize it and we double grow? So a lot of things are handled behind it, but user doesn't need to know, right? So you just say that I'm building a hash table and coming input is on this, and you can apply those aggregate functions, sum or count on other 2 inputs, and you can handle the overflow or not handle the overflow, and then where to execute. Target in this case happen to be GPU. And then it's a branch, when you go back to -8, so it goes back to the end of stream again. So that's a loop how you implement it, right? I hope I took some time to explain, but that's just a simple code, domain-specific code you can implement on this VM. So this is not to scare that user doesn't need to write it, right? I hope this is not the message you're getting. Users or the programmers or even data scientists, they are not writing this program, but the virtual machine has its own ISA, domain-specific ISA, which you can realize on any target. So as a result of that, our assumption is that world will be heterogeneous computing elements. We don't want to start a new project for FPGA, for a GPU, for tomorrow NVIDIA GPU or AMD GPUs or TPUs or some other processor at some other hooks. We would want to have a generalized virtual machine for the whole data processing, which is what we call data VM. And then underneath, you can hook up variety of the processing elements. So that picture looks something like following. You have a data VM. And then we have one more abstraction. You can ignore it. We call PDU, Programmable Data Flow Unit. But idea is that you hook up under VM, data VM, a variety of target elements, whether it's GPUs, multiple GPUs, or it could be FPGAs, it could be the CPU SIMD block, or it could be like Velox could be one of the, indeed in our case, one of the target for the SIMD block here. I hope this is clear. And then, so that's on the data VM. So now I have a virtual machine abstraction on top of my, on the heterogeneous computing elements. So what do I need on top? We cannot expect people to write that code. Obviously, in order to do that, we have another layer, which we call data OS, What it does is that moment those graphs on the left-hand side, we are familiar with that, input nodes, compute node, and edges represent the data flow. What data OS does is takes that intermediate representation like substrate, or we have our own IR as well, and convert it into the code that I just mentioned. It generates the code for the data VM. That's the job of the data OS. And most important thing, more than the code gen, we know that there is no one silver bullet. CPU's SIMD block has its own performance per dollar sweet spot. GPUs have their own strength. FPGAs have their own strength. Depending upon the availability, depending upon what function you're doing, this data OS decides at runtime. Remember I showed in the instruction there's a target. So it generates that, OK, execute this instruction on that target, not just on the GPU or CPU. So it does not assume that. So it assumes there is a heterogeneity at runtime based on performance per dollar. If I want to put that metric on that, it decides where is the right processing element for that instruction. And so on and so forth. And ultimately, as I said, Velox could be one, is one of the indeed integrated here in the data OS, and that's one of the targets. I just wanted to speed up given the time here, so we can have question and answer later on. So that's the middle layer. And the final layer is a lot of Binway and many of the folks have presented that there is a planner plugin adapter like Gluten, which is required to connect to the upper layer so that you're not changing, whether it's a Ray framework, whether it is a Spark, or Presto, or Flink, or whatever is a thing you want to have a common framework. As Gluten converts into substrate IR, that becomes the input to the data OS, for example. So data app, in our case, could be Gluten. It could be something else. We also integrate with Calcite, or it could be some other, as I said, Ray, as an example, is another one which we support. You can have it for the Gen AI or the AI processing workload. So it could be any framework where we can plug in this machine underneath. So just few remarks on that. Obviously, there's a lot of emphasis on that you stay in one domain, whether it's a Velox domain or the Spark domain, you don't do the fallback. But in the model that I just presented, it is inevitable that you would have to have multiple domains. So you would have to do domain crossing, because maybe there is a unstructured data processing engine which is inference-based or a model-based working along with the other engine that I presented. And in the same job, you are doing structured data processing and unstructured data processing, so you would have to do the domain crossing. That's the view we take. So that means how do we handle that, if you don't want to call it fallback, but a domain crossing between various domains, so you have to be more efficient. That means you have to have a common data format between them, so it extends beyond Arrow, which we have our own internal implementation, we can open source. And so there are a lot of things, emphasis put in with the assumption that there will be domain crossing, but how do we make it efficient rather than doing that, because those engines have their own sweet spot. Obviously, if it is you have to look over the data movement overhead, which you cannot avoid, then you don't want to have multiple domain crossing, but there has to be something like that. So that's kind of the high-level principle for this thing. Now let me switch last 3 or 4 minutes to talk about the second topic, which is called DP-mark. So again, this is just to motivate, and I had a casual conversation with a few of the folks here. And so there is a resonance of what this means, but it is up for discussion and so on. But here is an attempt or motivation. Why do we need yet another benchmark, what we call DP mark for data processing mark? So if you look at our typical benchmark, a lot of numbers are presented. They all start from TPC or predefined workloads, customer workloads or whatnot, right? So primarily today, conventional wisdom is that there are two things which determine the performance. One is obviously the quality of our plan, and the second is execution engine. If it is a JVM-based execution engine or a Velox vectorized engine or something, right? Those are the two things which determine your performance. High level, data movement, shuffle, and all those stuff are also part of it. But and we assume hardware is same and the same substrate because it has been same multi-core, 8-core, 16-core, 32-core, and some memory. And we lump all of them into performance per dollar characteristics. So the argument I think we are going to make is that that is not enough, because all of those, what the world we live in is now heterogeneous processor or processing elements, and there has to be a way to normalize their performance. We cannot just do performance per dollar because pricing is determined by a lot of other factors, not by there. And we cannot benchmark at the TPC level because the query planning or the execution engine also overwhelm it. So how do we put together whether the Ampere processor is better than Rivos processor, or whether the T4 processor or the L4 processor? Obviously, they have more peak flops. They have more high memory HBM bandwidth. better NV links. But what does it translate from DP point of view, from data processing point of view? That's the attempt we want to make it here, rather than just going over the peak flops and the paying dollar amount of the whatever. So that's the motivation behind it. So just one more comment I just mentioned. If you look at the complexity of heterogeneous world, what this DP mark should capture is that I'm just painting here 4 scenarios. The CPU-only system we know. You could also have a GPU-only system. But the others are when we have CPU and GPU together. So it's not only the CPU threads and the frequency, not only the GPU threads and frequency, but also the PCI bandwidth, my HBM, the high memory bandwidth, the GPU memory size, whether I'm doing spillover or not. There was a question in the morning, hey, is this only for SF100? What happens when it's FS1000 or SF5000? Then there's going to be a lot of spillover on the PCI for the data back and forth. How is that captured reflecting in the performance? Because those are all going to show up, not only the plan, but the execution engine. Similarly, if you have larger systems with multiple GPUs, then there's a cache coherent NV link, and you can gang up that 80 gigabyte times 8 into 640 gigabyte as a unified memory. But how do you take advantage of that? How does it reflect into the DP mark at the data processing point of view? Obviously, NVIDIA will say it has 640 gigabyte memory. I have so many teraflops or petaflops. But what is the equivalent number for data processing that we want to care about? So that's the idea. I think I covered this part that matters. So there are existing benchmarks like CoreMark, which fortunately, I helped define in my previous life, so for multi-core CPUs. And similarly, there are multiple benchmarks for GPUs as well. But I think there is a need for a DP mark, if I may go, at that level, not at the level of the query planning or things, so that we can normalize that, OK, if you're running on a DP mark 10, 2 machines, then it will say that, OK, then the system is performing different. Then we can have common characterization of the upper layers if we level set the processing elements on the bottom. Okay. So just few maybe what that should be. It's not a prescription, but based on our experience, it should be at a system level. System level meaning you can't say that I'll put the kernel in my GPU memory and just run the hashing on that or just do a sorting on that, right? That's going to defeat the purpose. It has to be a reasonable data size which fits into the at least host memory. So you also include the data movement over PCIe that I was showing in the previous slide, or if it is over NVLink, that data movement. So it has to be at a system level within a node, and it should have large enough data set. It does not fit into my caches or in memory, so that we are not making any vendor any unfair advantage to anybody with larger caches or smaller caches and so on. So there are a lot of thoughts we can put in. How do we define this DP mark? And most importantly, what we care is we know that ETL benchmarks have different operators. Then the BI workloads and emerging GNI workloads would have different operators. So there has to be some different, maybe 3 different DP mark, or we can have a geometric mean across those to give it a one unified number. Those things can be debated, and we can come up with that. So I just put in some samples of that, like ETL, BI operators, we know what they are. And for GenAI, I mean, we also support, for example, extraction of multimodal data, filtering, tokenization. So those are the things which matter. Those are the performance critical functions in the GenAI workload. So that means if you define this DP mark for general purpose data processing, not just for BI and ATL, then it might be useful to cover that also. So where do we go from here? I mean, I had casual conversation with a few folks here. I think there is a need to create a working group in some form, which will define the benchmark, data types, the data sizes. We can also define a process to benchmark and certify. The committee can also actually have a sample implementations so that people they have a sense of what it is doing. And then, and many things can be done. Actually, we have a version of this benchmark that we use for our internal purpose. We are willing to open source it. There's a Velox benchmark already part of it, and we have our own benchmark, so we can, if there's enough interest here or beyond this, we can define and open source our benchmark and the whole methodology and give it a name of a DP mark. That's an attempt. Okay, thank you so much for the attention. Sorry I took almost 3 minutes more than my scheduled time, but I hope this was useful. And thank you for staying so late on the second day. Thank you.
So I think you're going to be a part of the panel, so we can also open up questions there too, unless there are specific questions. Okay. We need a few minutes to prep for the panel to get the chairs and everything up here. So give us a few minutes. Don't move, though. And we're going to end on this powerhouse panel.
I know, right? They've really taken some
aren't they, like,
damage.
chewing on it?
I almost fell too. Same thing. Same thing. Even with like the colors and
They try.
All right, so let's get started. First of all, thanks everyone for staying here. I know it's been a long couple of days, but we really appreciate you guys coming, staying for the whole 2 days and staying until the end. Hopefully this can be a little more like a lighthearted conversation. We're gonna have space for questions, so if you want to ask anyone, if you guys want to be part of the conversation, we will have some time for that. I think we heard from most people here. I think maybe Zoltan was the only person who somehow didn't give a talk.
That's true.
Maybe we can start with a quick round of introductions, starting with you. Maybe just introduce yourself, and if you could maybe spend 1 minute just saying how you're involved in this whole hardware acceleration industry for data management.
Sure. Hi. So my name is Zoltan. I work for IBM Research. And I'm a software engineer working on GPU integration to Velox. So obviously this became for us also a good future outlook, right? To get hardware accelerated into Velox, because we see it also as a very good cost performance play, right? Not so much looking at the AI pipelines yet, but that's coming. But traditional SQL, right, is still a huge business. People still run traditional SQL. I know that hasn't been the focus of the last 2 days, right? But lots of traditional SQL still running, migrating to Velox, and I'm super excited about what hardware acceleration will bring to Velox.
Thanks, Zoltan. Felipe, do you want to go next?
Yeah, so I'm Felipe. I'm an architect at Voltron Data. I've been working on distributed SQL execution engines on NVIDIA GPUs for about 10 years. Just always been, wanting to work using CUDA, which is really hard to use, and allowing you to kind of stay ahead of the pack when it comes to performance. So I don't know. I've always liked working on GPU accelerated problems because it's just a lot more challenging than just working on the CPU. Yeah, that's me.
definitely very challenging. Rajan?
Sure, thank you. This is Rajan Goyal. I just finished my talk. I'm CEO and co-founder at Pelago, but engineer by heart. So my previous life, I've spent a lot of time on hardware software co-design, building domain-specific processors, MIPS and ARM-based processor for security, for data movement, and so on. But it's a much more fascinating world, I would say, the world of data, and it's becoming more and more exciting with the Gen AI and unstructured multimodal data. But excited to be here, and thank you for the opportunity, here, Pedro and team.
Yeah, definitely. Thanks for joining the panel. Greg?
I'm Greg Kimball from NVIDIA, leading the CUDF effort. And earlier I heard from Zoltan that he'd been trying to use thrust and cub to do some query processing. And that's kind of what CUDF does under the hood, actually, right? I mean,
yes, Philippe said it's really hard when you go down to CUDA and then cub and then thrust and then whatever in between, right?
And then you go from thrust to CUDF, and that's but you can kind of plug into the stack wherever you like, depending on how much patience you have. But we want CUDF to be a good for the low patience consumer who just wants to work in C++ and get things done. So, anyways, really excited for the discussion.
Thanks, Greg. I think everyone knows Ori, but Ori, do you want to introduce yourself?
Right. Okay. So I'm Ori from Velox. I've done many years of any kind of database performance-related stuff from the times MySQL was new. And then for the longest time, I was working on a system called OpenLink Virtuoso, which was kind of my baby. And that was anything from SQL Federation to XML to RDF, semantic web, linked data, if anybody ever heard of that. And then since the company was going for that to the exclusion of better pursuits, then I was at Google for a while and then joined Meta and studied Velox. And a relative newcomer to GPUs, I've done all kinds of performance-related stuff forever. Performance, I'm Challenger cat, I want to go for it. Climbing trees. So GPU is kind of the new tree to climb, so I'm a relative newcomer, but I'm trying to figure out the basics from the ground up and see how we can bring something new to this game. But it's a very challenging environment. It's very cool. I like it. And we're in excellent company with tons of talent and exciting stuff to do.
Cool. Yeah, thanks, Ori. We have this internal joke that engineers are like cat because they don't like to be told what you do, things like that. So Ori is the challenger cat. He likes big challenges. That's the context. Yeah, thank you guys for coming. So we put together this panel. We tried to make this as mixed as we could, having people sort of from different perspectives. We have hardware vendors. We have people building products on top of this hardware architecture. We have people from research community. We have users like Ori and me. So I think it's nice that we get slightly different perspectives on this whole space. I would like to start on a little bit more from the adoption perspective, right? So hardware accelerators, GPUs, ASIC accelerators of all sorts, FPGAs, they have been together for a while, and people have been kind of proposing and trying ways to use them in data management for at least a decade, maybe a couple of decades. So I'll love you guys. Could you comment on where you guys think you are from your perspectives on this kind of adoption curve?
Yeah, may I? Yeah. It's funny. You could look at papers published in the last 15 years, like up to I would say 2010, 2012. There were lots of papers about accelerating databases on GPUs. But basically, if you read all these papers, their conclusion was, oh, we're hitting the PCI limit, or we're hitting the disk limit, or we're hitting some network limit, right? So everyone was hitting kind of hardware limits. And then they said, okay, we can't do anything about it. That's hardware. We're going to wait for the hardware to catch up. And I really think, so from an adoption perspective, I think we're there where the hardware did catch up, mostly thanks to AI/ML, right? So we're just driving on the back wave of AI/ML innovation, which we can reuse for data. But also we're kind of late in a sense that lots of research have been done in the past that now we can use the same research and get much better results. So we should revisit what's been published, what's out there already to gain insight into why does that work today, right?
The engine's also changed a little. So at the very beginning, a GPU was seen as sort of this co-processor that you would pick a small amount of your workload and push it out to it, which meant you had to go over PCIe every time you wanted to do anything on the GPU. And then we started saying, well, now we're going to build pipelines, and we could do these 5 to 10 steps on the GPU. And now we're talking about accelerator native, where you don't leave the accelerator's memory unless you're spilling, right? So now I think that, in addition to all these things getting faster, we're also being smarter about how we build these systems.
I mean, it helps that the memory grew from 8 gigabytes?
2.
Okay, so right, or 2 gigabytes, right? Now we're up to, almost 200-ish, kind of, right?
So you're saying that you're moving from a place where you had accelerators for part of the engine, where now the engine is actually natively written for the accelerator. Interesting. Any comments?
Sure. Few comments. I think in order to make this successful, the problem has to be meaningful, which it is now. I would say it is much more problem to people are hurting if you don't do the accelerated computing. Cost is untenable. That's one argument. So it is a problem to be solved. You cannot ignore it by just running into some roadblock. The second is, as he said, the IOs are getting up, meaning improving. If you look at the improvement of the IOs in last 4 or 5 years, they are beating the CPU performance or the compute performance. So PCI or the disk or the networking, they are much steeper curve than the compute. So we used to 10 megabit or whatever, or those kind of network links. Now we're talking about 100 gigabit or even more than that. So the IOs have already caught up. So CPU is becoming a bottleneck. And the third thing is that it is not an easy problem. I think I just want to go back to the main question somebody asked. How do you handle spillover? How do you handle hash table larger than the GPU memory? No matter what's the GPU memory, you will always be 1/10 or 1/100th the total data set size. You still have to solve algorithmically, re-express your algorithms for this target thing. That is a very hard problem. You can't just, I'm just kind of stealing the word from Jensen and NVIDIA. He says, one of the challenges you have to re-express your algorithm for this target thing, right? That is not an easy problem to solve. So hence there are multiple technical challenges to be solved, PCI bandwidth, and as Felipe was saying, how do we be smart enough not to do the domain crossing and so on and so forth. But fundamentally, economics makes sense. B, the infrastructure is now much more available. GPUs are available every region, every data center, thanks to NVIDIA. The CUDA framework is much more mature, right, which for adoption of that, which was not there earlier. And most importantly, it is a time when customers are hurting. If you don't solve it, you can't just avoid it. The gap will keep growing. So the business is demanding for us to solve it. So, I think now it is up to us to solve it together as a community.
Yeah, no, I think that's a great perspective, right? So you're saying that the hardware platform has been advancing to a point where, now we have the right things. The science, it seems like we're already there. We already know how to build those systems. Then what's next? What's the next bottleneck for this?
And just maybe one more thought there. What helps a lot is that all the AI folks, they always want the latest hardware, right? So they basically, a new hardware architecture comes out, they want to move instantly. At least that's what I see, right? The AI guys I know, they always want the latest. So what happens to all the hardware that's been deployed, especially if you're looking at 2, 3, 4 year refresh cycles, right? All the A100s out there, they don't want it for AI anymore, right? Not for the AI training, actually, right? So all that hardware is now becoming more available. You'd be hard-pressed to get Blackwell or Hopper from NVIDIA, but A100 or the inference cards, they are plenty available, right? So this helps adoption as well, right? If you don't want to run it on the latest.
That's correct. Yeah, and just I think continue on that topic, now that we have the hardware, the right hardware platform, it's available even in public clouds, what is the next bottleneck? What's missing for us to move data management completely to this hard platform? Maybe Ori can comment on that.
Right, okay, so the good thing is, for many years, we've always said it was the next generation of GPUs that was going to be good enough. Now they're plenty good enough. Like Felipe said, A100 is fine, and they're available. The AI for us, let's say, the most expensive models don't make sense for data management cost-wise. So what we need is a mid-range GPU that's available in quantity. Of course, the scarcity is going to fix itself. There'll be more supply eventually. So that will sort itself out. The thing is functional completeness, staying within maturity, spilling, for example, staying within the accelerator domain. If you're on accelerator, you better stay there because crossing the boundary is expensive. And if this is going to be the only platform or the dominant platform in a data center, because we're procuring data centers now that are mostly GPU data centers, so if that's the only kind of computer you got, then you got to run all your work there, and this demands something from software maturity. Also, if you're going to build a data management data center as opposed to an AI data center, from GPUs, then you're not going to make the investment unless the technology is sufficiently mature. However, for smaller applications, the wide availability of that stuff on public clouds is going to be good because smaller applications absolutely can be deployed on clouds whenever the software maturity is there. So, like my call to this community would be, okay, let's fix the long tail problem and let's do benchmarks.
And I think maybe double-clicking on that point about workloads. I think, Zoltan, you mentioned that you and your team are doing a lot of work on just supporting more traditional SQL workloads.
Right.
I think there's this idea of sort of data consumption, right? Getting this data into dashboards. There's the idea of kind of transforming data in the warehouse, data pipelines, all the way into the whole discussion.
All boring workloads.
Yeah, I wouldn't say boring, but yeah, more like SQL analytic workloads. All the way to this discussion we had yesterday on kind of training, getting this data out of the warehouse, feeding into trainers. How do you guys see this spectrum of use cases, and what's a good target for those accelerators?
I think maybe we need a mix, right? Like Ori said, we need a mid-range GPU and build the data center with it. Maybe we need a mix. I think, it depends if you want to throw everything in one box, right? Which I don't think you can from a cost perspective also. If you want to push your training pipeline and your pre-processing pipeline together for the AI workloads, right? Then obviously for the training you want the latest hardware, which for normal data doesn't make sense, as we discussed, right? So I think you need a mix, but this mix needs to be on the, it can be in the same data center, right? But I think that's an open question, at least from my side, definitely. A GPU-only data center where you have one kind, I think that's hard, right? Because partially of the long tail and partially of the mixture of workloads that you're running.
Some of your workload, go for it. Some of the workloads are going to spend very little time moving data onto the GPU and then do a ton of computation on the GPU. And in those situations, we found that the more expensive ones are quite wonderful. If you're shoveling data across, if you're moving data from slow centralized storage to the GPU, the more expensive GPUs are almost never justified because you can't get the bytes into the GPU fast enough. You'll never fill it up. You're done processing and have moved on to the next thing and you're just starved for data. And that's where the older, cheaper ones have the benefit of, while the GPU might be older, well, the network cards got a little bit better, and the SSDs got a little bit better, and then the RAM got a little bit faster. And so all that sort of helps. It's like you're catching up to the accelerator with all of the other things around it.
Yeah. I think on that topic, another point that was interesting is, I think, Zoltan, you mentioned that historically the bottleneck was that we couldn't get data in and out of the accelerator fast enough, and now those things are catching up. And yesterday we're having a discussion with, I think Victor was also partly there. We're saying that the bottleneck in a lot of cases is actually the memory throughput on the device, right? So it seems like the bottlenecks are changing. And can you guys
just to, maybe for the audience, just to put some numbers on these bandwidth numbers we're throwing around, right? On the A100, you're looking at like 2 terabytes a second device memory bandwidth, right? And per GPU, you're looking at 200 gigabit towards the network, right? If you go one up to the Hopper series, you're looking at 4.8 terabytes a second device memory and 400 gigabit on the network, right? So you see device memory bandwidth doubled roughly, network doubled roughly, right, as Felipe said. And then if you go up to Blackfly, you get like 8 terabytes a second. I'm not shilling from NVIDIA, it's just the spec I know. And put it into perspective, like to PCI Express, previously you were happy if you could do like 10 gigabytes a second, right, on 100 gigabit. And now with NVLink, you can do 1.8 terabytes a second, right? So it's just hellishly fast. And so but the old stuff is fast enough, right? Like cost performance, as you mentioned, it doesn't make sense to put any accelerator there if you're just waiting for I/O, like the network I/O, right? And yeah, so just numbers-wise, I think these are the numbers. And for main memory, it's like 500 gigabytes a second. So the accelerator is already, between 4 times and like, what's that, like 16 times faster, right?
Can I make 2 comments? So one is just to echo back what Felipe mentioned, is that at architect level, you want to have an impedance match between your compute and the I/O, right? That's the problem statement. Obviously, in the beginning, I/Os were behind and it was not helping, but now I/Os have kind of improved. So ultimately, architecture level, within a node or across distributed systems, we are talking about distributed system here, you need to have an impedance match between your I/O bandwidth, whether it's a PCI or the DRAM or the network, with the compute. And if you look at from that perspective, and if you do that math, you will zero in onto the right GPU, which is kind of sufficient for that. And luckily or fortunately, that happened to be the lower end GPUs or more available GPUs, which is the good thing to have from engineering point of view. The second point I will make is that if you look at the historical GPU's evolution itself, when they started getting used for AI world, none of them had tensor cores, right? They were just designed for graphics. So people were still figuring out a way to use graphics-defined GPUs for AI workloads and so on, right? And that time, GPUs were not efficient design for that. But as workload became more prominent and important from NVIDIA point of view, all the modern GPUs have first-class citizen is inference or training workload. So they thought about how to define caches, how to define SMs, how to define their TLBs or whatever is all tensor cores, all defined for that workload. So my optimistic point is that moment we have the adoption with the GPUs with the current breed, and it becomes a prominent workload, as Jensen has publicly mentioned many times, I'm sure the next generation workloads will, GPUs will consider how do we handle the data movement problem, how to make that thing better for data processing workload, right? It is not as designed yet. We are trying to repurpose something animal designed for 2 other workloads into data processing right now and still trying to get value out of it. But moment it becomes big enough, I'm sure NVIDIA will consider, and maybe they added NVLink for something else. Why not have better PCI or hardware DMA or whatever to do this back and forth movement, right? And so.
But the scale of economies wins, right? Like some of the hardware builders, they can go and buy HBM in really large quantities, so it's cheaper for them, so they can build the card. That's why the second generation or the third generation behind, like the older generation, you can have cost effective, right? If let's say I start a startup today and I want to buy HBM memory, it's going to cost me a lot, right? And then of course the question is, can I do it without HBM? What can I sacrifice, right? That economies of scale help NVIDIA, AMD, and other accelerator builders because they have volume, right?
Right. We are getting the right hardware acceleration as it is because we have, let's say, decompression, which is a quarter of our CPU cycles goes to decompression, and what we hear is a Blackwell generation has at least some decompression in fixed function units, and the Rivas gear will also have something of the sort. So it's already coming. And now the question for us is, okay, if you can move data into the device at 20 gig per second, let's say over PCIe 4, what is the set of operations that you can keep doing on the device at an incoming data rate of 20 gig per second? And okay, so if your in-device data rate is like 100 times that, like 2 terabytes a second, then probably you can do hash join and group by and stuff like that keeps missing the cache all the time. Because you got to remember these super high throughputs are not random access, they're sequential access or data copy or stuff like that. But it's getting there, and we're really like at the threshold of maturity here. And what about workloads? Well, the AI adjacent ones are interesting, of course, because there we already have the equipment. And now the general purpose stuff we shall see. But it's our belief that we also, inside Meta, we want to promote this idea of using accelerators for general purpose data. But of course, for us, the most readily available is the AI adjacent workloads.
Yeah, I think I would like to touch on a topic that you, Rajan, you mentioned in your presentation, which is benchmarks. I think we keep like seeing benchmarks from different systems that run TPCH, TPCDS, different scale factors, different hardware platforms, different environments. It's really hard to kind of compare and see how they actually compare price-wise. So how could we do a better job? It seems like you guys have been putting a lot of thought on that, right?
So if I may just, one is a distinction between what are we benchmarking, right? Obviously, there is a discussion about what the next generation benchmark should be at the TPC-DS level, right, at the end user level. So that's a valid discussion to have, because TPC-DS today does not represent AI workloads or modern workloads. So that it needs to happen. The second point I was making in my presentation is that we need to normalize at the hardware level which hardware is better. Because right now we just had a discussion whether it's a better PCI bandwidth or better HBM bandwidth. All that contributes something to a application performance. And like in CPU world, we used to argue my core has, I think there was a question in the morning to Ori, mine is a 128-byte cache line and yours is 64-byte cache line. This is much better. I have 512 TLB entries, you have 128, this is much, but that's like a cherry picking a feature of a processor to predict the application performance, which is very hard. So that's the same thing I predict that is going to happen in this thing. My GPU is better than yours, or my AMD will say whatever, just to pick some names. In order to avoid that, I think there is a room to define a normalized name, could be whatever, Apple or Orange, but it's a DP mark, which is to say that, okay, if I have a two processor with DP mark 10, that means something from data processing point of view. Maybe both have tensor cores, we don't care, and we don't want to benchmark those. Maybe they have some other hardware, video encoder, decoder, we don't care. We want to only benchmark those processing elements based on what the data processing is relevant out of that, right? So that's what is the meaning of DP mark, so that I'm not even paying for it and I'm not even contributing. Some processor may say that I have a better video encoder, decoder. It's no use to the DP processing, right? I would want to discount that. So hence, I believe there's a need for a DP mark to normalize the various heterogeneous computing elements. But the second point is, yes, at application level, I think it's a valid debate to have whether TPC-DS has run its time, because it has so many variables, planner and optimizer and execution engine, which goes into making the, and it also is gap between it and the new application. So that, I think, has to be a different debate. So that's my view.
It is always really interesting how many signals come out of query plan differences rather than anything else. We've done a lot of comparisons of the Velox built-in plans versus some internal plans.
Correct.
And that ends up, like how you did the work, how you planned out the work matters more than the execution layer in a lot of cases.
Exactly.
So that's not going to go away, though, sadly, for the application layer. But in the micro benchmarks idea, that does have a, there's no complement that we have there.
I think there are 2 or 3 constituents to this topic. One is the end user, right? They don't care about my microbench, DP mark, or CUDF benchmark. They care about what is the performance they're going to get at application level, right? So for them, planner, execution engine, chip, they just care about performance per dollar. So there is and every customer we go to, we spend so much energy putting TPC-DS queries and optimizing. We show it to the customer, the guy says, I don't care. Move on, give me the performance on my workload. Nobody actually, zero customer, excuse me for that, but any of the customer we talk to, nobody cares about TPC-DS. They want it because everybody talks about it, and for us as a vendor have to work really hard to optimize it and show it. But when we go to the customer, they say, okay, forget all that, let's get in the door and let's do a POC on our workload, which is the right thing to do because it's not reflective of, I think that gap, if we bridge between having a synthetic benchmark which reflects a modern workload, lot of ambiguity between vendors and the customer will bridge. So that is much more important as well. But then the subsequent layers of benchmarks are more important for us, to builder of the platforms. Okay, are we doing apple-to-apple comparison? So that's my perspective on that.
Yeah, I'm very, very glad to hear that because, of course, having spent a lot of time on TPC benchmarks and they are extremely sensitive to you having the exactly right answer to the trick questions, and they're built-in trick questions. And I was designing the graph database benchmark LDBC, and we invented particular trick questions to incentivize this kind of optimization over the other kind of optimization. And benchmarks like application-level benchmarks as the TPC ones or the LDBC ones that we were making are just like that. And I don't know, can you entirely get rid of them or should you? Probably not. We think that this feature engineering benchmark that we've been talking about is a step in the right direction, but it's a lot of work and it's a lot of influence games to make it accepted. So it's refreshing to me that Rajan is talking about DPMark, because DPMark would go a long way to standardizing some things and making our implementations more comparable. I mean, everybody claims anything from 5 to 10x. That's fine, but these we cannot do very much with these comparisons unless we have much more context. And so I think this DPMark thing is a step in the right direction, and is a lower hanging fruit than redefining the next DPC benchmark for the AI age.
Yeah, I think that this idea is really strong, like normalizing whatever happens on top of the device so we can actually compare different hardware platforms. Yeah, I think that makes a lot of sense. And there's also the discussion of how we can come up with new benchmarks that reflect what people actually do, not what people did 20 years ago.
Exactly.
Which is another good topic in itself.
Right. I think that, just if I want one remark, that requires a discussion with the, actually in your case, you are on both sides. You are the user as well as the producer. So you are in a very unique position to reflect what user cares and what we care from this side, right? So, but having a communication with the customers and users, what they care about, where the workloads are moving, and do they care about performance per dollar or performance per watt, whatever the metric, right? So those are important. But I'm glad to hear Ori's comments also on DPMark. Thanks.
Yeah, I think we're in a very privileged position where we have the use cases and we develop the platform, right? So we can kind of co-design them a little closer together, but it's depends on the market you're in. Before we open to questions, I want to touch on at least one more topic, which is this idea of how do we extend those platforms to be actually not generalizable, but to cover a good spectrum of use cases, right? I think there's this idea that having something that can run TPCH, TPCDS is not easy but doable, right? But having something that can run every single workload with every single UDF and data type that can run everything from Spark, like that's a much longer journey. How do you guys see this idea of how do we complete this long tail and make those engines actually full-featured? And I think maybe Greg, because you've been working with libcuDF.
The approach that we're taking in cuDF with this is to use NVRTC in more places. So use JIT compilation to handle cases that aren't precompiled, rather than trying to, we have a few tools to do kind of arbitrary expressions in cuDF. We have an abstract syntax tree part of the library that steps through a tree and then processes it in a kernel per row way, kind of an interpreter kernel. But we've used it for a long time because you can precompile it, but it has a lot of downsides as well. So. Velox Wave has shown some pretty good ideas with JIT compilation, and I think that's going to be a big part of the UDF story. In Spark Rapids, they have a lot of they have to solve the UDF problem as well, and for the most part, they have to fall back or break things down to binary ops in cuDF where they can. But there's probably still going to be a role for CPU fallbacks for a long time for some of these particular operators, and doing that efficiently is great. We would love to have like kind of everybody contributes their 10 favorite UDFs into a pool, and we figure out how to accelerate them. I think that'd be a really valuable, without having to get into the certification and specification part. Just like let's throw out some UDFs that are maybe all Java and tricky.
That's kind of what we did with Velox, right? We had kind of the same problem. We started re-implementing some things, moving from Java to C++, and then we have the same thing, right? Like having hash joins and table scans. It's a lot of work, but it's doable. But then you have hundreds and thousands of UDFs to re-implement, and I think that's one of the areas where we got a lot of contributions from the community, and that's one of the reasons why we could move so fast, right? But then questions like we will have to do that again for GPUs and maybe potentially for other types of accelerators. And if there's a magic way to automate those things, that would be great.
Yeah, just to throw in one other thing. When you opened the panel asking about adoption, and my panelists up here started talking about hardware, I really got shifted without a clutch, because I think about that as a software problem for the most part, and making adoption painless and easy and complete and performant on this long tail is, we've got a lot of the hardware. We've got a lot of the bottlenecks in a good place.
It's a software problem, right?
Yeah.
Because of the AI wave, right? So it let us use the hardware. So now I agree, now it's a software problem, right?
Pedro, can I make 2 comments? So one is actually I want to underline what Ori has mentioned here as well as before, which is that goes back to the question you asked Pedro earlier, what would it take for adoption of accelerated computing to take off? Right, that's the question which is on our mind. We answered earlier from technology point of view, hey, IOs are improving, blah, 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 which is also true. I think there's a practical aspect of it because we are trying to apply a new widget or a new animal or new step function into a legacy problem, right? Which has a very broad spectrum of functions and operator and something. So I think it is a common goal for all of us to figure out how to bridge that tail function, that long tail that Ori says, how as quickly as possible so that they are all available and we catch up with that broad spectrum. So that's kind of the problem we inherit because it's a legacy application, legacy function with a broad spectrum. How do we bridge that? So I think that's a community level problem. And the second is, I mentioned in my slides, but I think this notion that we are falling back is true in today's context. But I want to argue that going forward, moment we have enabled 1+1 execution engine, Velox plus GPU, Velox plus FPGA or SIMD plus whatever, that means I do see a world where you would have domain-specific execution engines coexisting at the same time and being operated on the same job. Right? So you would have a PDF file being processed along with the structured data where you're doing a join on maybe join is happening on some other engine and PDF extraction is happening somewhere else. So that means the problem is not so much about falling back. The problem is more about how do we do the domain crossing more efficiently? How do we have a common memory format? How do we make the data movement more efficiently? So if you look from that angle, yes, fallbacks need to be solved for sure in today's world, but I think there is a bigger problem to solve so that we can have a more unified platform from structured data, unstructured data, and do we have
I think maybe dispatch is a better word than fallback because it's going to get more diverse. You know, we were talking, Binwei and I were talking about how gluten offers many different execution layers. So
right, you're agreeing.
Yeah, I'm agreeing.
Okay.
Yeah, so I think for in particular for GPUs or SIMD platforms, I think there's a possibility. I mean, composability is not entirely a pipe dream because particularly if your platform is such that it processes arrays and pointers, the ABI agreements can be quite simple. I mean, we just need to, okay, arrow is something. Okay, arrow plus string views, or like Pedro added his stuff to arrow the other year. String views and list views. That's pretty much it. If we can standardize on that, and then we can standardize on some policies for variable length data, and then we can standardize on errors, then we can have a pool of reasonably interoperable pieces of SIMD code that we can then JIT, and NVRTC seems to be the way to address this type of platforms, and Rivas is also offering a similar capability or even the same capability. So I think there's something to be enabled, to be unlocked in that space, and it's not an extremely high fence before we get there if we have like a desire to do that as a community, because I don't think any of the parties here is like super strong in this particular domain already.
One of the things that I think is missing for making all these things both real and excellent going forward is sharing resources when you use UDFs, when you use different systems. If you're going to compose a workload across multiple engines but share hardware, right now, I don't know how everyone else here does it, but the most common thing is, oh, I've got these two different things. I'm going to give you 20% of the memory and you 80% of the memory, and then we're going to go off on our way. But accelerators, while they have a lot more memory now, it's still not that much. And you still like have these really spiky consumptions. You know, it's not, you know, memory utilization, if you, even when we saw on Greg's slides earlier, right, the amount of, like, the GPU memory being consumed during the processing time is not constant at all. And so if we're gonna, if we want to like make real UDF someday and like have things, have these systems actually work together, they need to be able to say, give me a little bit more, give me a little bit less. Like, they need to be able to give that back without having to rely on something like just the driver, right? Which is, you can do CUDA malloc and CUDA free, but if you're trying to write fast CUDA code, you better never use those APIs except for once at the beginning and once at the end, if that's how you're going to do it.
Wait, are you saying that the hardware platform or the software platform should do that for you, or did the application view?
The applications need to do it. I think that, like, in my dream, there'd be like remote RMM, right? Like the Rapids Memory Manager, which would allow different processes to share resources. And there's all different kinds of ways that we can talk about doing that, about like, how you request an amount. Well, you can't always get it, or sometimes you'll have to wait longer. But
yeah, I mean, we did a lot of work in this domain in what Mong presented today in Velox. No, that's not for accelerators, but the problem set is very much the same. How do you manage like multi-tenancy between the conflicting demands? How do you regulate them? How do you police this situation? And that's something derivative of that work could apply in the accelerator space, and that's, I agree, a key part of the interop story or the composability story here. And I think we should all like sit down and see what would be like the critical unlocking factors for us to get this show on the road.
There's been some progress with shared allocators. Like I think PyTorch and TensorFlow both let you define an external allocator, and then if you can have a shared allocator, then you can, the process can work well together. I don't think we can share between processes, but if you can at least handle some kind of pre-processing before training, that's useful. I think in the AI data pre-processing case, though, it's going to need to be kept separate, because you can't ever let the training job. It needs to stay fed, so it can't fight with itself to use memory to feed itself. Like, it's just going to be too risky and unstable. I feel like to have it on the same node. What is your take on that? How much pre-processing can you put on the trainers?
Well, see, if the trainer has 80 gig or some multiple of that in memory, then it likes to consume batches of 1,000 rows, and if the rows are a megabyte a piece, then it's like 1 gig a batch or something like that. So it consumes stuff a gig at a time. And then if you can produce a gig at a time, consuming, let's say, another gig for intermediate results and staging and decompression and stuff like that, then out of the 80 gig on the A100, you would be using 2 gig for staging and decoding and stuff like that. I think that's an acceptable trade-off. So, and these are very much like fixed width stuff. The hash tables and things like that you have in analytics and ETL are the things that are unpredictable in size, and the group by cardinality, you don't know that ahead of time and stuff like that. And they need to be more adaptive, whereas the AI workloads tend to be like fixed width things that have a pretty set size and even want to process fixed size batches.
This is a much more bullish case than I was expecting. That's pretty exciting.
I think more practically, the sense we got from the trainers team is that they're very busy just making sure that the thing doesn't blow itself up. So I think getting to a point where we can actually share safely, it will probably happen, but I think it's a couple of years in the future.
I mean, you got to have fixed size allocations there, and you have a trade-off, and there's all kinds of contention there. But it's possible to do, because the whole thing is about having fixed size matrices and fixed size this and that and fixed size input batches. So it's a solvable problem. But the less solvable problem is the resource sharing in multi-tenancy query processing, where the needs are less regular and less anticipatable.
I think this is a very good discussion. We probably could stay here the whole day just chatting about this, but we did promise we would open for questions, and I'm sure people are dying to ask you guys questions. So if anyone, just there's a question over there. Please let us know if you're directing the question to someone or if it's just open.
Sure, yeah. So great conference, thanks for that. My question is for Rory. Yesterday in the Masha's talk, there was a description of why the AI workloads cannot be expressed in the SQL, and Ori also touched upon that today. Can you talk a little bit more about it, like how that language may look like? Is it gonna be better API in terms of data frame, or it's gonna be a new DSL language? It's gonna be imperative, procedural. Like, what's your thoughts on this?
I think I would you say, okay, SQL, the VP from IBM said SQL is king, and I like SQL. And if not SQL, then at least declarative, because declarative is what you can optimize, and declarative is what you can make inferences about, and declarative is what you can parallelize. So data frames, of course, you can interpret data frames as an alternate syntax for SQL. So the things that need to be expressed are things like this reversible functions, DS shift, mixing ratios of unions, certain ordering criteria that are not absolute. The mixing ratio I already mentioned, fixed size batches of output, so that if you have variable size batches, then if there's a small batch, the rows have overweight, and if it's too large, they are underweight, and this training is sensitive to that. So these are the sorts of things. I would say many of these could be seen to be flags to a window operator in SQL. Maybe that's where we'll put them. But as we now do have like a language play, we will be looking for ways of expressing these things in a declarative way that you can optimize and you can build a compute around. The solution is not entirely clear. There's also DuckDB has like syntax sugars that are entirely interesting, but do not really speak to this expressivity question. So we'll be blogging about this, and we'll be designing stuff for that. And we hope SQL process is exceedingly long, so I don't think these will make it into any standard in the immediate future, but they will make it into some implementation of ours.
And if I may add, I think in a way the language discussion is even a little less important, right? What you want to do is you want to have the plan and execute that efficiently. Now, if that comes from a SQL statement or a data frame or some other imperative language, you can even provide many of them and kind of for different use cases. I think as long as you can get this plan and you can execute that efficiently, that's I think the thing we care about the most. And with that said, I think all the training things, at least that we have internally, they're all data frame. The discussion is usually that, like, could those things be unified, and could you also support SQL? And I think in general the answer is yes, right? Again, the integration point is usually the plan, not the language itself.
Thanks.
Other questions?
Polars did a pretty good job allowing you to do optimization on a data frame plan with the collect operator, their lazy frame abstraction. Pretty cool.
What is that name?
It's in Polars.
Polars.
My question for Raj, you mentioned that I/O now catch up with communication. This is the reason you created your company?
Sorry, can you repeat?
You said the I/O can catch up now with computing.
Yes.
Or communication catch up with computing. Is that the motivation for you to create your company?
No, that's not the only one. And it's not a futuristic statement that I/O will catch up. I think the point we were making, collectively we were observing, that if you know Moore's law, that was for the computing side, for general purpose CPUs, has stopped or has flattened or is dead, whatever people
Slow down.
Exactly. So it is not like you're not doubling the performance of general purpose CPUs every 18 to 24 months as it used to happen earlier. So that's one thing, but that has not slowed down for accelerated computing. NVIDIA is a perfect example of that. That has not slowed down for IOs. Your PCI bandwidth, your Ethernet bandwidth, or network bandwidth, and memory bandwidth, those are still improving on that. So if you look at last 5 to 10 years of if you plot the charts of how the Ethernet has improved, the PCI has improved, the memory DDR5 or high HBM has improved, and put the plot with the CPU performance, you will see that those are like rocket ships growing exponentially, but the CPU general purpose computing has slowed down. So that was the point we were making, that I think he was making that there was a gap early on when the GPUs were there and the I/O was becoming bottleneck quickly. Now it is not. So that's one point. But if I may want to use this moment to explain why we formed Data Pelago, that was more that CPU alone is not enough. We are born into this heterogeneous computing world where you will have a variety of processing elements. And all the existing data platforms were designed a decade back for different world. So in this new world, there is a need for a new thinking, a new platform, which is a function of what we just talked about, right? So that was I hope I answered your question. Yeah.
So the GPU doesn't follow Moore's law? GPUs?
Well, it does not. I mean, if I may want to say that way, because if you look at empirically, it has been improving performance every generation to another generation, so it has not slowed down, right? So if you look at the NVIDIA's last, I think Greg can speak much more.
You're doing a great job. I don't want to stop you.
Yeah, and I'm happy to say about that. But yes, if you look at the NVIDIA's last 18 to 24, whenever there's a GTC conference, yet another is the new GPU with double the performance, right? So double the cost. But at least performance is definitely doubling and improving, right?
So how did you manage to do that, Greg?
Oh, it was easy. Let me tell you. No, it takes a really long view and a huge talented team and a global team to do it. And yeah, I can't. I'm not qualified to speak to the origins of NVIDIA's success here, but but it involves a different programming model. It's if you look at the clock speed of the threads in a GPU, that's following Moore's law.
Yeah, I can answer offline. I don't want to hog this time here, but yeah.
Yeah, I think we only have a few more minutes. Let's take maybe one more question, and then we can wrap up. Deepak.
Happy to take the last question of the conference. So one of the other harder problems I see is also profiling. Like, how do you, so current tools, you have one tool for like CPU, one tool for GPU, and maybe one tool for a specific hard accelerator. But I think like when you combine all these, it's going to be much challenge to understand where the performance is, going. So what do you guys think about that problem? Like, do you think we need a tool that sort of combines all, or a new paradigm?
We at least need one that can cover multiple GPUs and multiple nodes and CPUs simultaneously.
Wow, it's really hard.
NVTX does that already, no?
It's tough when you have a cluster and you have to manage a lot of data comes out of that. What we need is a hardware accelerator for hardware accelerator profiles.
If you eat your own dog food, you can do it.
I know.
That's the way to do that. But
Yeah, automation of Insight Systems data is a thing that we're working on in my group and working with the Insight Systems team on a bit as well. They're trying to add more automated tools to work through this to get the thing that you need. Like earlier we showed table scan breakdown of I/O, decompression, and decode, and that's automated, derived from profiles, but that's not part of the mainline thing yet. So there's definitely a gap, and we need to, we haven't solved the multi-node thing, how to manage the.
I don't think you can do it on the driver. It's too much information. I think that if you really want to do this well, it must be directed by the builders of the engine using things like OpenTelemetry or other tools that capture the metrics that you want at the granularity that you need them.
NVTX is pretty great though. Zoltan has a good point. You can attach data to it now. So
you can, and I do that all the time, but it slows down my process, so I'm not actually getting like my real times.
Yeah,
right?
That's true. That's true.
And it will literally change what your bottleneck is because of that overhead. So now you're not seeing that interesting piece of information. Like I think that, by the way, I love like NSYS, right? I use it all day long. It's a wonderful set of tools.
NSYS is awesome. Yeah.
But for what's being described here, I think that we've got to do some of the work ourselves, because the engine builder is the one that knows like what they're trying to track and when they're trying to track it and how much they're willing to pay at every single stage to get that information.
I don't know, Deepak, do you think we should add operator stats in Velox?
And metrics maybe?
Yeah,
Yeah, sounds good.
We have so many of them. I mean, Wave adds some 10 new runtime stats and all that stuff, and NSYS is great, but it's very localized information. What are you going to do to particularly distributed things like shuffles? How do you measure shuffle performance? How do you measure lost work because of latency of this? Or skew of that and stuff like that. So these are not GPU-specific things. GPU makes them a little bit trickier because you have still more and more and more of these counters, and there's more counters than you can follow. So you could try a machine learning model to summarize the counters. I've been dreaming, decades long over an expert system that would just say, okay, what's wrong with my program? What's wrong with my query? Why is it slow? And I mean, there's common causes of slowness. It's not impossible to do. And maybe now with better machine learning or stuff like that, we could just train it because, the training works well when you have infinite examples and slow queries are plentiful. So
yes, that's true. All right, I think that was the last question. Just to wrap up, I just want to finish on a very positive, forward-looking note. So maybe we can go around the panel, and if you guys can just share your view, like on the next, let's say, 3 to 5 years, what's the next breakthrough? Like, what are the things, the kind of interesting things that will happen in this hard acceleration space? And we started with Zoltan, so let's start with Ori and kind of go backwards now.
Okay, so my prediction is that accelerators will be it doesn't have to be predicted. They're getting to be everywhere. So the challenges that we'll see is that nobody can program that stuff. And the model of programming models and things like that Triton, OpenAI, and people are doing may be good for something, but they're not there yet. So we do need to educate the public. We do need to find some way of multiplying this very scarce pool of talent. And these are some of the minus side. On the plus side is that the gear is there. It's becoming increasingly available. The problems are there. The data is plentiful and is only getting more so. What's going to happen with AI? Is AI going to come to our rescue for generating these programs that nobody understands? Probably not. So will be the thing to see, but it's going to be exciting times, and I think we will see, if not like all around mass adoption, we will see certainly increased validation of our proposition with accelerator-first computing.
Cool. So what are you saying that in 5 years we're going to have AI helping us program those things?
Unlikely. Don't quote me on that. It's a joke.
It's been recorded on YouTube, so on VeloxCon 2030, if anyone is watching, send Ori an email 5 years from now to see if he was right. Greg.
I'm really hopeful about where Velox can go in the next 3 to 5 years as well. There's always a push towards fragmentation in data processing. I don't know if it's getting worse over time or if it's just always really rough and up and down the stack, new experiences coming in. I hope that we can get more unified in the next 3 to 5 years. I hope that Velox can grow and succeed and have more backends available to it. I hope CuDF can be a very powerful backend for anything Velox wants to do on GPUs, and then we can grow up from there. Make sure that the gluten and Presto C++ layers are giving Velox the information it needs to run everything that's coming in from a wide diversity of front end sources and all kinds of applications. I think that it's something we're talking about here. But it's gonna take there's a lot of software that we have to build to pull that off, and but yeah, I think Velox is pushing in the right direction there, and Velox and CuDF share goals, and we're both pushing in the same direction. I think we're gonna do it.
Nice. Yeah, I think that's I think one of the things we discussed for Velox is that if we could get to a place where the sort of execution in data management becomes more of a commodity, like in operating systems, right? You just use Linux. If you want to compile things, you just use C-Lang. If you want to run things, you just run on Velox. So let's see, 5 years from now, let's hope we get there. Thanks, Greg. Rajan?
Yeah, so I think I'm, as I said in my beginning sentence, is that I spent last 15 plus 20 years doing accelerated computing for security, for data movement, for deep packet inspection, and building other stuff. So I don't think there is any escape. And physics is physics, right? So Moore's law has stopped for general purpose computing. So you have to have accelerated computing for this problem as well. There is no escape for that. Data is growing growing like anything, becoming complicated. Applications are all becoming data-driven. So you have to solve this problem. And I think we will solve it. So I'm very optimistic about it, and it's going to continue that. So that's on the adoption of that. There are challenges, how to debug it, how to profile it, how to have a common memory management. I think those are technical problems, how to have better sorting or better hash or spillover jobs. I think we can solve it together collectively. So that's on one side. Just on a fun side, my prediction will be that maybe the 3 years, 5 years from now, VeloxCon we can have in Vegas. We may need multiple hotels to arrange it. But I wanted to also take this moment to thank Meta team and Velox team to hosting us. It has been a wonderful experience last 2 days. So thank you so much for having this presentation forum.
Yeah, no, thanks for joining. We've been discussing about maybe doing that in China next year. Vegas came up. We also talked about Hawaii. Let's see, maybe.
Hawaii.
Hawaii would be cool. Can do the beach.
4 votes already here. Yeah.
All right, Felipe.
File formats. My hope. So I don't know if anyone noticed, but up on that screen, when people were showing their workloads, like 60 to 70% of the time is scanning the data. And of that, 2/3 of it was decoding and decompressing. Holy smokes. Like that, you know, we've spent so much time optimizing joins and filters and all this kind of stuff, and then building incredibly complicated file parsers and decoders and decompressors. Like, look at the read parquet. We were talking with some NVIDIA people earlier, and literally it was mentioned, right? Like, look at the read parquet code. It's quite involved. And I think that hopefully what we're going to see is file formats that have accelerated decoding and decompression built in, vectorizable, like where the format itself is meant to be read and processed quickly and not necessarily optimized for how do I compress the most amount of bytes into a thing, or how do I make this easy for humans to understand.
Absolutely. So we did have this file format club for a long time, and this was really the #1 point on our agenda. And we do have Nimble, which is already better in that regard. And we got good work at CWI in Amsterdam that have fast lanes, and these are very GPU friendly. So this is widely acknowledged by the community, and let's talk more about it.
We just need to push Nimble through the finish line, right? We have the right design. Yeah, and then trust me, I think the pain points of encoding, decoding is something we've been seeing more and more often. I had a whole presentation yesterday about this. So yeah, we can definitely see that. Thanks, Felipe. Zoltan, do you want to wrap it up?
Yeah, I think I would take the other side of that bet with Ori about AI helping us. We're building the systems for AI execution, right? I think in 5 years, maybe we can have that expert system helping us. You just throw there your slow query, you have no idea why it's slow, and build the system that can actually fix itself. I think with the growing compute, I think this might just be possible in the next 5 years. So I'd really like to see that.
Almost like a vibe SQL coding of sorts.
Yeah, vibe SQL coding, exactly. Just explain what you want and let the system build a nice distributed
Get your trademark
system.
in now.
All right. Well, thank you. Thanks, everyone, for joining. I know it's getting already late. Hope that was useful. I'm also hoping you guys are going to stay here at least for a few more minutes. So if you have any other questions, anything else you want to discuss, just come here up front and chat with the specialists. Thanks, everyone, for coming. And Ali, if you want to wrap up.
All right. So we're going to wrap up here. I just want to say thank you. I hope, like me, you all are feeling so excited, and what a wonderful community that we've built up here, and it's just so incredible. So thank you for 2 great days of Velox. I have to give some quick shout outs. This thing was put on by volunteers. This wasn't anybody's full-time job, and so we had a lot of Meta engineers, IBM engineers that kind of took time out of their real jobs to put this thing on. So quick shout out to the Meta team, Pedro, Sridhar, KK, Krishna, IBM, Deepak, who helped put this thing on. It's a lot of work, and so really appreciate it, and I think it was an awesome 2 days. All the Meta volunteers, the engineers that are out there escorting people back and forth, make sure you get escorted out if you're leaving, by the way. Thank you to them. I mean, that's 2 days of their time, so really appreciate it. Thank you. Thank you, guys. Thank you all to be here, too.
Just want to thank Ali. She was our fierce leader putting this event together. It takes a whole lot of work, so thank you so much. And hopefully we're going to see each other in 6 months in China or in Hawaii or Vegas or something, someone a little more fun. Thanks everyone for coming.
Ines, I think one thing I want to close out on this, right? So thank you so much for being here. This was a great event. Thank you for amazing presentations and being there for over the two days, right? So as part of the volunteers club, we definitely would love to thank our AV group. Did a fabulous job over the 2 days. And our culinary group for giving us amazing food like beverages, keeping us energized over the 2 days, and our security and facilities team as well. So thank you. Without all of you, this would not have been possible. And Ali, you ran the show. Amazing. Cool. We'll see you next time.